Good morning. Good morning to all of distinguished scientists, professors, academicians, research scholars and students. So we have third day of the International Conference on Photonics and Emerging Materials for Futuristic Technology. This conference is best organized by Department of Physics. I want to congratulate the organizer for inviting very learned speakers. So in this session, we have a very learned speaker, Dr. Anil Kumar Chauhan from BARC, Mumbai. I request him to take seat on the dais. Dr. Anil Kumar Chauhan, he will speak a lecture on organic devices, perovskite, solar cell, energy, supercapacitor, environmental remediation, and I have the opportunity to introduce Professor Anil Kumar Chauhan. Professor Anil Kumar Chauhan joined the Baba Atomic Research Center, Mumbai in 1993 after completing a 1-year postgraduate training program in physics from BARC Training School. He completed his PhD in science from Mumbai University and carried out his postdoctoral research work at Institute of Electronics, Microelectronic and Nanotechnology, University of Lille, France. He is working in organic devices and has published more than 100 research papers in international peer-reviewed journals and has more than 120 conference presentation to his credit. He is the recipient of IF, CPAR and DST JSPS fellowship for his research. He is the head of the organic device section in the technical physics division of BARC and professor of physical sciences at Homi Bhabha National Institute. Recently, he has been appointed as officer on special duty, Department of Atomic Energy at Branch Secretariat, South Block, New Delhi. So we are very delighted to hear a very learned speaker. I invite him for this lecture. Lecture timings are 25+5.
Thank you, sir, for introduction. First of all, I would like to thank the organizers for giving me an opportunity to speak some of our work, which we have carried out over a long period of time. Actually, I was a student of CCSU University and I always feel proud coming here whenever I get a chance. I was a student of this physics department long back. Maybe some of you were even not born there that time. In 1992, I passed from here and joined BRC training school. And actually, this was a very good, or I would say I was an ordinary student when I actually entered this campus. This campus made me extraordinary. And I'm extremely thankful to this campus and I always feel coming here. So with this, I start my talk on organic devices. See, like in BARC, we have like BRC structured in different groups, and then from groups there are different divisions, and the mandate is mainly actually to develop the devices, and this is development oriented. Research is actually a secondary thing. R&D is basically to develop certain devices. So I will go briefly. I will first introduce little bit of my division. I belongs to technical physics division, which is actually associated with the development of materials or mandated with devices, beam lines. We have actually, our division has developed 4 beam lines which are at Indus 2 RRCAT. 4 of the beam lines belongs to our division in Indus 2 and 3 at Indus 2, and then development of analytical instruments. Then the work towards the growth of applied physics domain in the areas of crystals, detectors, gas sensors, solar cells, thermoelectric, synchrotron instrumentation, and UHV based surface analytical instruments. Our section, the mandate of this section is to carry out R&D towards fabrication and characterization of low-cost organic devices such as organic solar cells, organic memory devices, organic thin film transistors, organic LEDs, organic thermoelectrics, and photodetectors. So, in the beginning of my career, actually, I started working on single crystal radiation detectors, and towards last 15-20 years, we have been in the organic devices. So these are my colleagues. This is me, and we have two physicists, two chemists, one chemical engineer, and one assistant in our section. These are the some of the facilities, not all. We have a globe box where the chamber itself is having a very good control of atmosphere, and the moisture and oxygen level inside this is controlled up to 0.1 ppm level. So, the organic devices basically which are moisture sensitive or atmosphere sensitive, they are actually we make inside this only, and then everything starting from the chemical preparation to the device formation, including the measurement, is done inside this. Then we have certain characterization equipments which these are all, you may be aware of many of these. So, recently we have carried out certain works. Actually, as the theme of this session is solar cells or energy devices, so mostly I will be speaking about the solar cells only. But some of the work which we have carried out, which is notable, is the we have developed super hydrophobic polypyrrole films. These were required for specific purposes in our department, where certain super hydrophobic films need to be replaced with the organic materials. So, we developed these films on the basis of a polypyrrole. Pyrrole was polymerized to make polypyrrole, and this film, it has been deposited on the you can say stainless steel substrate, and you can see it is a super hydrophobic film. Then also in dye-sensitized solar cells, we know that the counter electrodes play a very important role, and which is actually of platinum material. So, which is very expensive. So, we replace platinum with the polypyrrole as a counter electrode, and we developed a special method using electrochemical processes where the TCOs, the transparent conducting oxides, that can be actually patterned. So, these are for if you want to make certain devices, then patterning is absolutely necessary. So, we have developed a method for patterning those things. Then various organic molecules or conducting polymers we have studied for towards objective of like having organic field effective transistors, organic memory devices, organic gas sensors, and organic dielectric materials. We have all these devices, not all but most of the devices require TCOs, that is transparent conducting oxide material. Means you have a material which is transparent also and it is conducting also. So, normally the conductors are not transparent. So, so we have like made this by this process silver nanowires which we are using as a, we didn't use much, but we use for certain so some time, but we are still working on that silver nanowires and transparent conducting electrodes. And then similarly the polypyrrole also which we used is also used as the TCOs in certain things. We for our department, like radiation detectors, especially for neutron gamma discrimination is required. So, this also we have developed a process in last 2 years where we developed the plastic scintillators. So, with this now I come to my talk, which is basically on the solar cells. So, what are the solar cells? Solar cells are those devices that take light energy as input and converts into electrical energy. So because there are mostly students, so I have tuned the talk in such a way that it gives the both flavor of research also and flavor of little understanding also. So what is the source of energy? It is actually sun. We can consider it as a hot body which is at 5800 Kelvin. So by our basic physics we understand that every hot body emits the radiation, and at this radiation, at this temperature, the radiation emitted, black body radiation emitted is exactly like this. So, and what is this? Is what we actually receive on the earth. So this energy which is fall on the earth is nearly 1,73,000 terawatt of sunlight which are received every day, and this is more than 10,000 times of what actually is requires. So if we can somehow tap this energy and convert tap this light and convert into energy, even 10% or even 0.1% fraction should be sufficient to produce everything, all the power. So for this purpose, solar cells are devices which converts light into energy, as I already said. So solar cells are basically, these are in three generations divided. The first generation solar cells were wafer based. These things started in the 70s or 60s. These are basically monocrystalline silicon or gallium arsenide silicon solar cells, and then afterwards it came to polycrystalline also, which has a little lower efficiency. These solar cells were used of high specific applications. Then second generation come, which were basically thin film based, where less material is used, and these are amorphous silicon, cadmium telluride, CIGS kind of solar cells. This is now the recent, you can say current generation, which includes organic solar cells, dye-sensitized solar cells, perovskite solar cells, and quantum dot solar cells. So first let us try to understand how a typical solar cell works, how it converts the light into actually electrical energy. So this, all of us being a physicist know that every solid which is having a long range ordon, it's a single crystal, it has bands. So the bands are valence band and conduction band. So suppose we take silicon, which is the most commonly material used in the solar cells. So and then we have p-type solar cell. P-type means the Fermi level is slightly lower. N-type Fermi level is near to the conduction band. Now when we join these P and N junctions, what happens? So you join them, but now when you join the Fermi level, there is a large difference in the Fermi level. So the Fermi level difference cannot be abrupt. So what happens? First, electron holes moves. The Fermi levels has to be aligned. Now Fermi levels are aligned, so there are actually electrons and holes on both the sides. They will try to move the other sides. So after some time in the thermal equilibrium, it will not remain an abrupt junction, but with the Fermi level, though it is not absolutely straight, but for the sake of understanding, we can consider it. It becomes like this. Now you see there is a voltage difference which has been created between this point and this point. This is called as built-in potential, and this built-in potential is actually responsible for the movement of or you can say extraction of electrons and holes which are generated there. And now we connect these two through this external circuit, and with this circuit the current can be flown. Now if we connect a metal directly with the insulator, with the semiconductor, will it transmit? Can anybody tell me? Will it translate the current, or you can transmit the current? No. Why? Because now it's a semiconductor, it's a metal. So there is a metal semiconductor contact. There will be a Schottky diode here, there will be Schottky diode here. So there will be two back-to-back Schottky diodes, so there will not be any current transfer. So what we have to do, we have to make the ohmic contacts. There is a specific technology for that which we will do. So now suppose light falls, electron hole pairs are generated, and these are, because of this built-in potential, they are transmitted and they flow through the external circuit. Now, the photovoltaic energy conversion involves 4 basic steps. What are those steps? First thing is that the photon has to be absorbed. Now, when the photon is absorbed, this excited energy has to be converted into electron and hole pairs. Those electron and hole pair has to be transported to the external circuit, and then this has to be collected, and through the collected charge carriers and electrodes, and that these has to pass through the load. So this is the entire process. So all these process has to be absolutely efficient if you want to make an efficient device. Any one of them can actually just veto. If anyone is not working, then your solar cell is not going to work. So BARC is mostly mandated for the things. So when our space program was initiated long back, and because of certain things there was an embargo, we were denied the solar cells also, and solar cell is very essential part of the satellites, because that is the only energy source of the you can say energy in the satellite. So the work was assigned to us. Okay, can you develop, though we are nuclear, but can we actually make solar cells? So the technology of the solar cell was developed in BARC, and so this is the typical process in which we made. So the diffusion of phosphorus to make 0.3 micron thick N-type layer on the top of surface, and then front and back contacts were made. Actually this looks very simple, but the technology was very tedious. So all this technology was developed, and this is the recipe of flow chart of the technology which has been developed. And these are the solar cells which were actually this kind of panels were prepared, and a typical panel containing 60 solar cells of nearly 1/2 centimeter square with this rating, these were supplied to the space ISRO at that time. And some of these panels are actually the part of some of these satellites which were actually sent. But now what happens when you develop something, or you show that you have a capability of development something, then people start giving you the things. So they though we have developed everything, we transferred the technology to BHL Bangalore in 84. These things actually got died afterwards, because we have then supply of the solar cells. But these solar cells, these photographs are actually of today's photograph, and these things are developed in 80s. We still use these solar cells. Now, some people have doubt about the silicon solar cells, how these solar cell, can these solar cell work for a longer period, or so. I give you an kind of practical example. This is a solar cell which I have taken from the earlier stock, and the data is taken from the technology transfer document for this particular solar cell, and this was the value of this solar cell in 1984. The open circuit voltage was nearly 0.6 voltage, short circuit current was this, fill factor was this, and efficiency was 13.7%. Even after 40 years, the same solar cell, exactly the same solar cell is giving this parameter. Though its contacts are, you can see here, they are faded, little bit of the back contacts are not that sharp, and some things are, the front contacts are also not that good, but still it is giving such a high value. And now then we did the other things also, the radiation hardness of this solar cell, because these are being used in the space, so no change in the parameters were observed up to 10 kilogray of the irradiation of the ionizing radiation. Then the input intensity also, because when it is in a space, it sees a lot of you can say harsh conditions. So Then we varied the intensity from 5 milliwatt to 300 milliwatt, but the performance of this solar cell did not change. The temperature variation was also, we tested plus minus 70 degrees centigrade, it was fine. So till date, those devices which were actually developed in 40 years ago, they are still available, they are working fine with almost similar efficiency. So don't doubt. So now the question comes, when everything was developed, everything is available so well, silicon solar cell is working too good, then why actually organic is required? Because there are certain issues which are there with the inorganics. What are these? First thing is, it's expensive. High purity materials are required. You need high purity, you can say semiconducting materials, and the processes, fabrication process is also very difficult, complex. These are not flexible, heavy also. They contains a lot of weight. In many places you cannot actually apply. And some solar cells which are use cadmium and like silanes, these are toxic also. So can organic solar cells be a possible alternatives? Yes, because it has certain advantage. It is going to have a low cost. If you ask me right now whether it is low cost, the materials which we are using are really low cost, they are not, because they are made specifically for the purpose and they are made in a small quantity. But when you have found a perfect material combination, then it will be obviously very, very cheap, dust cheap actually. Then these are good absorber of light, easy processing, flexibility, can cover large surface area cost effectively, tunable properties, eco-friendly, and most important, being a physicist, we know it very well, there are infinite possibilities. Why infinite possibilities? We have only few semiconducting materials, silicon, germanium, and there are certain combination which we use as per our convenience, second, fourth, third, fifth, something like that. But they are also limited. You don't have more than, but their specific properties are also fixed. Everything is fixed. Everything is understood well. You cannot alter much things. There is not much tunability is available at cards. However, for the organic materials, once you find a semiconductor, you can change its property. First thing is you can make a conducting to a semiconductor move. So there are infinite possibilities of the molecules. You can change the band gaps, you can change the current carrying capabilities of the molecules. So when everything is looking such good, there are some problems also. Why it is not still available in the market? It is not available in the market because it's an evolving technology. It is not yet mature. There are a lot of problems, not stability issues. Efficiencies are poor. They are going to remain poor, because it's not a like semiconductor inorganic. Degradation and stability issues, batch to batch variation, then material purification is difficult. So these are some of the problems. So before going to learn about the organic, first we understand what is the basic difference between an inorganic material and organic, what we are actually trying to gain. We should not expect everything from the organic. We should be having some realistic image in our mind. So what is inorganic? We know it's a single crystal. Single crystal means, and you can say an long range order, starting from the one end to the every end, the crystal is same. It is a perfect. So once an electron reaches in the conduction band, it doesn't belong to that particular you can say atom. It becomes to the entire you can say crystal. So once you excite an electron from valence band to conduction band, it is ballistic from one end to another. However, why it is so? Because it's a long range order, the band is formed because there is a long range order which we have, everybody has studied Cronin-Penney model and the further band model. So however, so once an electron and hole pair is generated, it is almost free all the time. However, this is not the case with the inorganic, because it is very difficult to make a single crystal of the entire material. So they are going to have clusters. cluster. So if you have a cluster, the maximum width of your band will be, it depends on the size of the cluster. So you are not going to have a band like this, you are going to have a small bands. So these bands are actually not, we call it valence band and conduction band, but scientifically they cannot be valence band and conduction band. They are called as the HOMO and LUMOS, that is highest occupied molecular orbital, lowest unoccupied molecular orbital. So now what maximum can be done is you excite an electron from this place to this place, and now see there is a discontinuity, it is not continuous. So maximum the excitation, the electron will remain only from this point to this point. It has to be actually transported in order to have the conduction throughout the material. The electron need to be transported from this place to the another place to the conductor. So you are not going to have electron and hole pair, you are going to have excitance. Excitant is electron and hole pair which is bound. So in the similar way, which like I did it last time, how a polymer solar cell will work, I will give a similar like in the first animation. So you have, now we do not call them P and N, we call them donor and acceptors, though the things remain same. So when you connect them together, under thermal equilibrium, the Fermi level is supposed to align, though it is not exactly the straight it is, but for understanding we consider it's like, now if a photon is absorbed inside any of the things, it can be absorbed within donor also, can be absorbed within acceptor also. So you are going to have the electron is going to be excited from the valence band to the conduction band, not in the term of these things where we call HOMO to LUMO, but it is not going to be a free electron hole pair. It is going to be bound. So its tendency is actually to combine, because the most probably it is going to combine, it wants to, the electron will come back from this place to this place and it will combine, they emit the same radiation. Now there is another problem, though there is a, you can say there is a slope, it seems that it will reduce the energy from going from this place to this place, but it is actually not seeing, because this is a charge neutral entity. It's a electron and hole pair. So neutral charge, it is not going to see. So it can move in any direction. It can move in this direction, this direction, this direction, and this direction. So probability is still false. But let us consider in the most, you can say the best scenario for us, that it moves somehow. It moves and it reaches at the, you can say junction. Now this junction, this energy difference provides a, you can say, provides it a sufficient, you can say, driving force to actually so that electron and hole pair separated. Now actually this has electron and hole pairs are separated. Now because they are separated, they can see this slope and they can move like this. So you have seen many things which we have presumed as per our convenience. What is first was that okay, though it is charge neutral, but it will move towards the junction. Next is that it will conduct very smoothly through this entire thing, and this size is also we consider as infinite, though it is very small, it is size of the cluster. So can we make a device which was like a silicon solar cell, a traditional device using the organic material? So in place of like donor I use as a P layer, and acceptor I can use as a N layer, and I make exactly the same device like here acceptor and donor, and I can make it should be exactly this replication of the silicon solar cell, but it doesn't work. The efficiency of this device are the best is actually 1%. Normally it is 0.1, 0.001%. Why it is so? That as I said in the earlier one, though the thickness is more, but most of the excitants which are created in this range or this range, they will be lost. So only the excitants which are created during this region they can reach the junction and get separated, and then afterwards, even after they are get separated, there is no guarantee that they will reach at the electrodes. So now what we can do actually, this way it's the end of road for us. No way we can make any organic devices. So then the approach came as the bulk heterojunction. What was that approach? See, if we cannot go to the junction, let the junction bring near to us. What was that? You blended donor type and acceptor type material, we blended them very finely, so that it is structure like, so now you have a boundary which is actually much more area considering. So then we don't call it a P type and N type separated, rather than we called it a blend of P and N, and this is a called we active layer. And then there is a P dot PSS is a hole extracting layer, and this is an electron extracting layer. So it's the same thing I have written, the whatever I have explained. So P dot PSS is like a whole transport layer, which is very common. So now how do we make, or how, if you want to make a device in your lab, we do it in this way. So this is a ITO coated glass. So it's a glass, over that a transparent conducting oxide is you can say deposited, which is available in the market. How much time, sir, have you? Okay. So then this is conducting, transparent, so light falls from this side, and then it is patterned by chemical etching. So certain part is actually with the tape, it is covered and dipped in the acid. Then after removal, you get only this part of the you can say electrodes. Then the whole transport layer of P dot PSS, it is deposited by the spin coating. Then you deposit active layer, and then do a little bit annealing. Active layer means it's a BHJ, which is blend. Then you deposit electron transport layer over it. Then make the other electrodes. So now in the same set, you have like 9 devices. One device this way, one and this device. So in the like you have make 3 by 3 electrodes. So you will have in the same experiment you make in you can make up to 9 devices. Now for each of these separately, you can make connections, and after making connections, you can actually do the measurements. So what we understood, so we have certain things which we can play with. What are things to play with is the anode, which is usually anode and cathode, which are usually metals. We cannot play much with them. We have standard work functions for these materials. If you are using gold, it is always 5.1. If we are using aluminum, it is 4.3. We can't change that. So these are like levels of donors and acceptor. Probably we can play with that. And so these are the 4 levels which with those we can play. And we can select the materials which are basically give these values. So now the absorption of any photon, we know it depends on the band gap. If you have a 0 band gap material like metals, it will absorb totally, but it is not going to give any output in the form of solar cells, though it will absorb everything. So we have to make a certain, so this gap actually it tells how much it will absorb. So absorption is governed by the band gap. The open circuit voltage, which is the maximum voltage which can be generated by solar cell, it is governed by the HOMO level of the acceptor and the LUMO level of the donor. So this difference, actually difference between this point and this point, it will give you approximate value of the open circuit voltage, which is the maximum your solar cell can generate. And then the short circuit current is, it depends on these levels, actually how close these levels are there. So when there is a resonant transfer, then this current will actually flow through this. So we can so by playing these levels, we can actually find out. And then last is charge collection. You need to select these materials. You cannot use aluminum in place of gold or any material of your choice. So these should be matching with the energy levels of the donors or acceptors. So what we did, three strategies which we worked on: favorable alternation of HOMO-LUMO levels, improving conduction through active layers, and improving absorption in active layers. I will quickly go because of the shortage of time. So we started work on the poly-3-axial thiophene, which is a polymer, P-type or donor material. P-type I say because mostly we are actually from the inorganic side. So, and then PCBM is a acceptor molecule. This is a polymer, this is a molecule, and then we use graphene as a So see, graphene sheets, the thinner and shorter nano sheets were exfoliated from the graphene flakes. See, it is not easy to get graphene sheets, but flakes are available. We took these flakes from some other labs also, and from our own lab also, and from these flakes actually the nano sheets were exfoliated, but this exfoliation was also very difficult. So because we had to take continuously more than 30-35 days of the ultrasonic process. Then the composites were prepared by a long blending of the polymer molecules which are under dark. So now once you have prepared a polymer, how to find out what is the HOMO and LUMO level of these? These are basically on by cyclic voltammetry. So with the cyclic voltammetry, you can see with the onset of this oxidation peak, which was actually 0.56, it has increased to 0.69. So by which we can say, but for the P3HT it didn't change. So we found that the energy level actually which was the HOMO, which was for P3HT, it was 5.21, and these were the value which didn't change. However, for PCBM, which was molecule, it changes from 6.1 EV to 6 electron volt, and similarly for this also the HOMO level will change from 3.83 to 3.67. So if we you can say plot it again, so we can say the level which was actually here for original PCBM, it has gone up slightly above, and similarly this also it has gone little up. So now we can expect that improvement in open circuit voltage, and because it has come closer to this level, so short circuit current also. The conductivity is also measured by EFI SSG method. What is that? It is the electric field induced second harmonic generation, which is you illuminate it with the 1100 nanometer, and because of the change in susceptibility, it gets converted into second harmonic generation of 550 nanometer, which is actually mapped at CCD camera. So this is the typical real life actually image of how the electrons and holes are moving. This is a movement of within. So so it is from this point to this point, it is total 10 microsecond. So this was for P3HT graphene, and it was for pure P3HT. So with this we can see that it has actually increased. The conductivity has increased. With this, if with the modified blend, if we made the device, which has given you can say much better and improved efficiency, which is nearly doubled. When I say doubled, I have not given a figure because different kind of devices give you different figures. If you have a flexible, the maximum efficiency is about 6%. But if you take the hard like ITO coated glass, you can get up to 8 to 9% of the efficiency. So the thinner graphene sheets, this I have already explained. So the next is, I think if I have exceeded my time, maybe I can 5 minutes. I'll cover the remaining thing. So one was altering the levels. Another was actually the improving the absorption. How you can improve the absorption is basically you are increasing the thickness of the absorption. You can do it by simply reducing the RPM, which if you people have done, you will be aware, but reducing the RPM doesn't give a uniform structure. The next we did was we deposited layer by layer structures and increased the thickness. how we actually found that thickness has actually you can say increasing uniformly. So this was one was absorption spectroscopy, which gives you this spectra, and this absorption value will give how much amount of you can say radiation is absorbed for this particular wavelength. Next is the AFM. With the AFM also, with the tip you can find out how much the thickness is this. Next is the there is a one more method which we use, but that was not so reliable, but we compared with all the three methods and found that as you go on increasing the layers, the thickness is actually increasing. So when we say a single layer device, the voltage, the open circuit voltage was about 0.5453, and the current was very high, As you go on increasing the number of layers, though the open circuit voltage is increasing, but the you can say current is falling. So overall, if you try to find the total overall efficiency was actually reduced. Why it was reduced? We proposed that it has been reduced because though you are depositing one layer over the other layer, but there is actually no continuity, crystallinity continuity. So there is a gap. So it provides a you can say charge trapping for the electron and holes at these places. This was confirmed by impedance spectroscopy, because in place of single you can say semicircle, we have got two semicircles. We could fit with this. So one was actually we can say because of this resistance, the another was because of these layers, and the third was additional due to the you can say imperfections at these layers. So we did it by solvent annealing. Different methods were tried for different solvents, and then with the THF we found that with the help of THF these things could be reduced, and so we can expect that your the layer has become perfect. And it was confirmed by like impedance spectroscopy with a semicircle, perfect single semicircle, and it could be fitted with the a single RC circuit with the contact resistance R1. If we go like same thing, now the solvent annealing process was applied on both the layers just to ensure that are we making any mistake or our hypothesis is correct. So if you have a single layer, so before solvent annealing it was giving actually the voltage was almost same 0.53 and the current was nearly 16 milliampere per centimeter square, and after solvent annealing though the current was voltage was increased, but the current was reduced. Overall efficiency fall for the single layer device. However, for the multi-layer device which was having up to 5 layer, before the solvent annealing the voltage was about 0.5 EV and the current was about 7.6, and it has increased, the voltage was also increased and the current was also increased. And so the efficiency was actually increased by nearly 20% to the original device, not in the second one. And then we did some encapsulation studies on the device also. So devices were, because ultimately you have to use in the you can say market, not in the lab. So it need to be working. So if you have an you can say unencapsulated devices, you can see some of you may be making the solar cells who are working, and you find that within say 40-60 minutes or 1 hour the solar cell actually stops working because of the so this was actually there. And then after the epoxy sealing and the UV treatment, we could see that the devices actually has worked up to 40 days plot, and these devices are actually working for nearly 6 months, which we have seen. So these are the conclusions which actually I have already summarized. These are the some of the devices which are made in our lab, and they are stable devices up to 6 months, but not more than. This is a typical you can say demonstration. This is a solar cell which we have made. This is our lab only. This is a light source. It's a normal LED light source जो हमारे घर में होता है. And these are 2 fans. So if I can just show you, the light will glow and you can see this is a lab made solar cell, and this device has actually worked for nearly 4 months at the same place we kept before it actually died. I thank some of my seniors from our lab and Dr. J.V. Yakmi, who actually initiated this activity in 2006 at BARC. And these are the people I have used some of their labs for my experiments under DST, JSPS. With this, I am ready. Sorry if,
So we had a very fine lecture. It was a very informative lecture for solar cell manufacturing, and I hope that there should be many questions, but due to scarcity of time, we can take one or two questions.
and I'm sorry, sir, I exceeded
No,
10
it's
minutes.
okay. No, it's okay. Actually, your lecture was so good. If there was no time constraint, we should have attended for the whole day.
Sorry, sir. Thank you.
Hello, sir.
Yes.
Sir, my question is why they have very low efficiency?
See, for low efficiency for the organic, है ना? Organic perovskites or all these classes of you can say material, low efficiency. See, मैंने जैसे आपको explain किया कि see efficiency कहाँ से आती है? There are 4 things. One is the absorption. The entire light should be absorbed. Even if you have absorbed the maximum light, you can have 100% efficiency is 1 kilowatt per square meter. अभी क्या है? When it actually it goes into electron and hole pair. When you use silicon, it's a perfect material. Huh? You get electron is there and it goes immediately to contact. Very easy. But if you are using any of the organic material, first he has to cross many boundaries. First it has to pass from this, you can say, cluster to the another cluster. Then it will go to the another cluster. Then it will go and see there, okay, whether my electrode is actually matching. Should my energy will fall going to the electrode. So there are a lot of actually problems, or you can say hindrances, which stops electron and holes moving from one place to another place. That eventually gives, you can say, reduces the efficiency. Efficiency reduction is only because of these 4 steps are not actually very favorable in the case of organic materials. That
I
includes perovskite also.
I think you must have received your answer, and due to scarcity of time, we are not able to take more questions.
There I can,
we will have you can have more discussion during lunch time. So now I invite Professor Anil Malik for. So on behalf of the organizing committee, I thanks Professor Anil Kumar Chauhan for giving this very valuable and informative.
Thank you, sir. Thank you, sir. And I'm sorry I extended my time. Thank you, sir.
So, हाँ सर का फोन सर सर आपका सीवी अच्छा So now we are going for next lecture. Next lecture is to be delivered by Professor Suman Mahindia from Kurukshetra University, Haryana. The topic is engineering nanoporous materials for energy application. And I got the opportunity to introduce her. Professor Suman Mahindia is a professor in the Department of Physics at Kurukshetra University. Her expertise is focused on energy applications using porous 2D nanostructure materials. She also researched on plasmonic nanomaterials for SERS and polynanocomposites for EMI shielding. Dr. Mahindia has an impressive record of 50 published papers, 3 patents, and H index of 21. And she has also guided 6 PhD scholars. She has been highly honored, including recognition by the Governor of Haryana and receiving the American Chemical Society Award. So I invite her for this lecture. Professor Suman Mahindia.
Good morning, everyone, and thank you, the organizers, for calling me for delivering my work and can interact with you. So, okay, yeah, sure. So, the topic of today's talk is engineering nanoporous material for energy applications. So, just within a seconds, I'll go through the home tour for the Kurukshetra. So, I belongs to a land of Dharam Kshetra Kurukshetra, or you can say land of Mahabharata. So there we are having a man-made Brahm Sarovar, which is a very wide and very deep also. And today only the International Gita Mahotsav has been started there. And then this is our lush green campus, Kurukshetra University. And these are the 2 main gates of the university. And we are having heritage of the Haryana Museum in the university known as a Dharohar. And this is my department, the Department of Physics, and this is our department, and these are the major facility, in-house facility in the Department of Physics. This is a 200 kV accelerator, that is low beam energy ion accelerator, and these are the facilities been in-house there in the ion beam center. And then we are having some other facilities that is inside the Department of Physics also. Majorly are in my lab, and these tools are related to some DST fist facility in the department. And the major work related to my research group is for the development of the electrode these days, from the biomass for the supercapacitors, asymmetric battery electrodes. Then we have done some work related to the utilization of the plasmonic nanomaterials for the water splitting, photoelectronic water splitting, and then we are having some work related to the sensors also. So today's talk is related to the biomass valorization and their engineering through some activation, and then utilization of these biomass related material for the electrode applications for super capacitor. Mainly today I am focusing. So we know that globally what we are facing the 2 major problems related to the energy crisis and related to the waste management. So how we can realize to make the evaluation so that we can generate something good by resolving the 2 major issues. So the whole of the problem is related to the waste to wealth, and through the waste management we are generating some wealth in form of the energy. So we know that this is a Ragon plot, and related to the energy density and the power density, we are having the capacitor, well known capacitor. We are reading it from the school days to the graduation to the master level, and utilizing in our day-to-day applications also. So it is having a very high power density, but the energy density is very, very small. So it may act as some fictitious battery for a small duration of a time. So there is another class of a supercapacitor. So this supercapacitor, I am talking about how we can work and what are the mechanism related to it, which is having a moderate power density and the energy density that lie between the another applicative technology, that is a battery technology. So whole the work is related to what I am going to present is related to the supercapacitor mainly, and the target region for the future direction, how we can grow in that, how we can meet the requirement of the today's life. So it is in between how we can make an asymmetric or a hybrid of these two systems. So this is the overall comparison related to the supercapacitor and the battery. There the power density and the energy density comparison on that way. So supercapacitors is having a good power density, but related energy density is very low as compared to what we are getting from the battery. Rather than a battery, we are having a low power density. So just to back up, we can have the hybrid system of the two. So this is the mechanism classification. Let's start it from the electrostatic. We all know about that. Within electrostatic capacitor, what is happening? We are having a two metal plates, and through the polarization of the dielectric material inside of that, we can have the induced charge being generated at the metal plate, and so that we can have a storage. So the capacity is depend upon that kind of a storage. And in the electrolytic capacity, what is that? Metal plate is separated with through the electrolytic salt, and through the kind of the ion flow, we are having the storage mechanism. Next, we are having the electrochemical capacitor. Rather than a metal plate, we are having a porous carbon over here. So I'll go through the history of that also. And within a porous carbon, then we are having a sandwich layer of our electrolyte material. So this electrolyte material, what happened when we are applying some kind of a potential across it, we are having a generation of an ion, and through the porous carbon, it liberated to the electrode. So through that we can have this. So there is a formation of a double layer, which is the main mechanism happening for the electrochemical capacitor. So this is a brief history of a supercapacitor. It took almost 150 years to come up to this stage, so that everywhere we are talking about the supercapacitor, hybrid system, batteries all over, we are having the DC storage capacity. And this is started from the 1740, where the first such kind of a capacitor made the groundwork for the future. And then almost it took a century, more than 100 years to come up with some kind of a capacitor, which is through the foil of the electrode, and within that we are having the wax impregnated water paper dielectric capacitor. Then in the year of 1957, Becker just prepared and just gave it the kind of the capacitor which could be having the capacity in term of a farad. But the real mechanism was not known at that time. What has the mechanism, why that kind of a porous carbon is giving such much of the high of the capacitance. Earlier we are talking about in the micro and the millifarad, but that time, the first time the farad comes into the picture. Yes, we can really realize on the farad also. Then there are the companies Yo-Yo and the NEC which come up, and the today's also which we are coming across to get such kind of a good capacity with the competitive energy density near about, not exactly like in a battery, but near about like in a battery. So through this, so there is a two kind of the material, basically a pseudo material and the porous carbon, and depending upon that kind of material, their whole chemistry is different, and based on that there is a Faradic process and non-Faradic process for the charge storage. So whenever there is a pseudo material which is known as a Faradic active material, we are having the redox reaction comes into the picture, through which we could have the transfer of charges across the electrolyte to the electrode. And within the corresponding porous or the EDLC material, we are having the non-Faradic. There is a formation of a double layer, and through the double layer concept, we could have the storage. This is again the kind of the GCD and the CV curve based on the there's non-capacitive Faradic, capacitive Faradic, and non-Faradic capacitive storage material. So these are the class of, based on the supercapacitor, we are having the EDLC class, we are having the pseudo material, and then what kind of the material could be chosen to work on the different class of the supercapacitor. So these are the kind of the supercapacitor. We could have the coin cell, pouch cell, stacked cell, wound capacitor, and the stacked cell. So our main focus is to resolve the high capacitance, to attain the high capacitance. How we can do? It could be done through the, when we can able to tune the porosity, or we can just make the porosity to be happen in such a way that we could have the good capacity. So hierarchical porosity we are playing, and then our next job is to enhance the specific energy and their power density also. So this is just, I'm going through the porous nanostructure, because in the EDLC material, porosity plays very important role. So what kind of porosity we should have? First, we are having these three classes of the porosity, that is a microporous and mesoporous and macroporous. So basically, depending upon the dimension, what we are talking about, less than 2 nanometer is a microporous. So it is a old nomenclature we are talking about, rather than it should, today's it should called as a nanoporous. So just based on that, it is that if we are having a pore size less than 2 nanometer, then we could have the microporosity and mesoporosity. If we are having the pore size between the 2 to the 50, and then we are having the macroporous. So when we need the charge absorption and desorption within the electrode material through the electrolyte, so we should have some micro, some meso also. So it is important to play with them, how much of the micro, how much of the macro, and what is the hierarchical intercalation corresponding to these micro and mesoporous. So what we can do, these are the some images of the different pore size from the literature. So we are talking about the porous nanostructure. So first discuss about the some nanostructure we could have. So we are having the 0-dimensional nanocarbon, 1-dimensional nanocarbon, and the 2-dimensional nanocarbon. And under these class, we are having the carbon dots, carbon onion-like structures, CNTs also, graphene, reduced graphene, graphene oxide, like of that. And another class is the activated carbon, charcoals, and the template out of it. So again, it is a hierarchical porous structure. So our main focus is in the lab is for the biomass valorization, and make it to derive for the latest technology. And one of my project is related to the battery application, utilizing this nanoporous, making the hard carbon, making through it for the biomass valorization to the battery application for the EVs. So this is again the flow chart depicting how we can play it with that. So there are the mainly two process, physical activation and the chemical activation. We are focusing on the chemical activation because high yield and good hierarchical porous structure we can control over that. So they are the different kind of the chemical activation chemical we can use. Each one is having their own advantage. So primarily we in our lab we are focusing in the KOH and the ZnCl2 whenever we are having some heteroatom doping. So we are preferring to work with the ZnCl2 because it acts as a that dopant material reservoir, a bank reservoir for that. So that kind of a chemistry we are playing, and using that we are able to make the proper porosity material. So another kind of the classes, yes, we are doing with the plastics waste and the tire waste in the lab also. From the plastic waste and the tire waste, we are also generating the good nanocarbon, and in some of the batches we are getting the good graphene like structure, near about 7 to 8 number of the layers, not the like single layer. So these are the utilization of the carbon nanomaterial for the different battery or you can say energy devices. So this is the supercapacitor. It is also known as the ultra capacitor, electrochemical capacitors also. So focus is corresponding to the small material like low quantity material and with the good capacitive behavior and also the good storage ability in term of a power and tuning it to make a good energy density material also. This is the main mechanism that we could have. So EDLC was a complex material. Through the classical DFT it has been given that through the bulk solvation and solvent correlation we could have the key findings related to that. So what is that? It may be having the Columbian non-Columbian interaction, then surface charge de-elimination corresponding to that, then there is a transfer through the species, then how we can transfer the kind of thing. So basically it is the charge stage. So there is a formation of inner IHP, inner Helmholtz plane, and outer Helmholtz plane, and depending upon the more detail, it is having the three model we can work out. So we are having the single layer that is correspond to that. Next model is the GC model, where we could have the diffuse layer, and then the Stern model is a combination of these two, which explains how the solvated ion and unsolvated ion helps in the formation of a double layer, through which we are able to get the capacitance very high in the farad region. Then there is a carbon anomaly also. If we are talking about the size is below than like nanometer size, a few nanometer. So like carbon anomaly tell us about that nano size could not able to give you the more storage capacitance. But people have identified that there is no such kind of a case because of the quantum behavior maybe, or because of something else happening to that, we could have the good capacitance also. So through this we can play with the with the porosity, and these are the kind of the formulas used for the calculation for the electrochemical properties. So our work is, what I am focusing mainly on the activated carbon through the flower based and the seed and oil biomass. Reduced graphene also we have prepared from the different Hummus method, modified Hummus method, and some more modification from the Geo, and then plastic and the waste are recycled nanocarbon. Then we are making some composites with the magazines also, some graphene and the activated carbon, and then symmetric electrode, yes, through the Zn and the magnesium doping also we are able to tune the kind of things. So this is our work, and which is also patented under the patent application and published also. So we all know about the Genda fool. Likewise here also we have using it, and whenever you are in India you will see that there is a large applicability of these Genda fools for any kind of your academic, administrative, in the temple, for your religions also, in your house also you are using. But what happened after they use? We just dumped it, and this dumping is creating such kind of a waste that is harmful for our aquatic, if we are not doing the proper waste management for that. If we are just dumping it, it releases some of the gases, some ammonia, some, because it is rich in the nitrogen content. So how we can resolve that kind of issue? So we provided one solution. These are the kind of the organic material present in that. So we are playing with that. So for that purpose, we did some kind of lab routine experiments related to ZnCl2. We did with the ethanol soaking, without ethanol soaking, whatever we have getted, and just doing the experiment, what we realize is that with the KOH also we did, with the NaOH we did, but with the ZnCl2 what we are getting, that kind of a nitrogen doping it is inherently having. So we can tune its functionality with the ZnCl2, which is not possible through the KOH with the NaOH. That we have done the small experiment in the lab also. So it acts as a bank for the restoration of a heteroatom like nitrogen, and it play very good for the quinol also. In the quinol we are having very good amount of the potassium. So that potassium is also very good electrochemical charge transfer property also. So this is the BET analysis, and here we are getting for different concentration of the ZnCl2 with respect to our precursor, that is a volarized Genda fool material, and we are getting up to the 1200 meter square per gram of the specific surface area, and we are having the good meso to the microporous, and also which helps us to retain the charge capacity. So these are the XRD, and through which we could have, it is amorphous in nature, we could have that kind of a disordered nature, and we could calculate the LA, that lattice strain corresponding to that. Functionality also done checked through the FTIR analysis, not going in a detail. This is the important, that within a XPS what we have identified, that within a ZnCl2 and playing the concentration of a ZnCl2 with our precursor, we could have the change in the polycondensation of the aromatic ring. So from the Qn to the P5 to the P6 of the N structure we could have, and that helps for getting the huge capacitance out of it. So these are the deconvolution through which we can just identify what kind of the functionality and how it is tuning with the change of the concentration also. Similarly, we did it for the oxygen also. So basically this ZnCl2 is a dehydration property which act as a dehydration agent and causes the gas gasification for the oxygen and the hydrogen group, and remaining what we are getting the kind of the carbon structure. So pure carbon structure, not exactly pure, but the reduced functionality of the oxygen corresponding to that. So this is what very particularly we did it the XPS with the temperature related effects also we have done it to identify how much exact amount of the oxygen, carbon and the hydrogen we are having and the nitrogen we are having, and identify through the EDX concentration also. So what we have that get it from that, we are having N6 which is a redox active agent which helps in the electrochemical process, which causes some pseudo effect, and that through this pseudo effect we could able to enhance some energy density out of it. And the major component that is in the aromatic carbon form that helps for the storage of that. So we need to know about the true mechanism of the charge transfer through such kind of a pseudo material or pseudo doper. So these are the SEN through which we have identified it. So electrochemical behavior, this is a lab tested material. We taken the pure graphite substrate and over that we have deposited. These are the brush coated, and later on we have a blade coating unit in our lab also, so did it. So this is a basic lab based devices through which we have uses the 6 molar KOH, a salt in water effect, and then did the CV analysis out of it. We are getting the 179 farad. Although it is not very good, because these days people are getting very good near about the 300 and the 400 related to the asymmetry, but through the pure carbon without of any additive conductive agent, we have not using the carbon black, the pure activated carbon that we have generated, through that we are getting the 179 without of any external agent, and very good capacitive behavior at the slow scan rate to the fast scan rate, different current density also we have done the measurements. So over that, due to the N, because of the heteroatom, what we are getting some pseudo effect. So that pseudo effect is important to find out, and how much of the capacity is through that pseudo or the dopant material heteroatoms. So through the TASTI approach we have calculated it, and through which we could able to identify how much is the EDLC component, how much is the pseudo component over that. So we are getting very good supercapacitive kind of the GCD curves, very small ESR also out of it, and good specific capacitance through the GCD and the EIS also. So basically what happened, we are having a quinone, and then which through the ZnCl2 it reforms the N doping from the pyrrolic to the pyridinic. So basically if we are having a good pyrrolic N, so we could have the two way of the redox reaction, lone pair transfer and the proton transfer. However, if we are having the pyridinic N component, then we could have only either of the lone pair, either of them. So it will be having the one. So within that, what we have done, we did the engineering to get the more pyrrolic N. So that kind of a job we did through the ZnCl2, and yes, through which we could able to get the good combination. Then we have developed the coin cell out of it also, a closed cell, so that the electrolyte may not dry with the time. So what happens, we generated and getting very low ESR 5 ohm, and then connecting in the series, and we could able to glow the LED out of this supercapacitive material to the 3 minutes. I am again stressing, we have not added any kind of the carbon black out of it, and this material is recently published in the Journal of Energy Storage. Next is the homemade kajal. Everyone in our ancestor time we are talking about the kajal which we are making in the home. So that kind of a kajal we are using, just the kind of the reagent, little bit of the change in the reagent, we could able to make the good capacitive material out of it also. So again, these are the structural characterization. This is the XRD and the BET. Although what you are getting there, we are having the specific bet area is related to the 1200 something, 1200 74 meter square per gram. Here we are not getting very good specific area. Here it is up to the 700, but still we are getting very good capacitance. So this is because of the good connection of the meso to the micro, so that it will help to make the good flow of the charge. If we are having a very good big size of the meso pores you are having, so then it will be having the coagulation of the all the ions through the electrolyte. If you are having the kind of the slow tunneling kind of a behavior, so that it will help you to continuous flow of your electrolyte charge. So good charge transfer help you to make the good capacitive electrode out of it. So these are the electrochemical performance of this. Here we are getting almost like 227 of the farad per gram of that. And we could able to the red LED's resistance is very much high as compared to the blue and the yellow, and that time is near about the 2 minutes, and it is published, and in the know-how it is transferred to some of the technology transfers also we are in the process. And yellow LED we could able to glow with the 5 minutes to the 23 seconds, and this is also published. And then we have made the graphene like material, not the graphene exactly, so I'm not going in a detail of the kind of the chemistry and the physics behind the graphene. So as we know that हम लोगों ने बहुत ऐड सुनी है, दाग अच्छे होते हैं, सुना है ना, बहुत सारी ऐड आती है सर्फ एक्सेल की कि दाग अच्छे होते हैं. For what chemist and the physicist, yes, in the graphene on the 2D materials, that kind of a dag, what we are talking it, this dag is a defects. So those defects are very important for us. Some of the time we are generating the color center out of it, some of the time here we are using that kind of a defects for the charge storage also. Yeah, just in a quickly I'll just go through what we have done. These are the literature over that. So this is a simple modified Hummer's method geo we have prepared, and from the geo the routine kind of a graphene that everyone, those who are doing on that, we are preparing it. So yes, we are getting, we have checked it through the EDLC, through the aqueous and the gel electrolyte, and we could have the kind of not very much but 54 of that. So farad. So it is a binder free material. We have earlier we have used the PVDF as a binder. Here we have not used any binder. Direct application on the current collector, and the work is published and having a very good side. Then we have modified it. We are getting very low capacitance. We can enhance it through some manner. So what we have done, a conventional RGO, then we have done some microwave treatment, and then through the some kind of a redox functionalization, that is a hydroquinone we have done, and through which we could able to enhance, these are the characteristics, we could able to enhance the specific capacitance, and that capacity, this is a small demonstration out of it. Why it is not working? So we could able to glow the LED much more larger time as compared to the normal graphene that is prepared through it. So this is through which we are making a charging, and we could able to discharge the 3 in series coin cells that is fabricated in our lab only, and make it to glow for the next 3 minutes. So this is a full demonstration. Once it discharged, we have just released the connection and connected through the LED, and we could able to glow it. So this is also under the patent, and the conventional RGO work is also published, so through which we could able to glow it. Here we are getting with the microwave, we are getting 180 farad per gram. Here we could able to enhance from the 54 farad per gram, we could able to enhance to the 210. And this is work recently published. Then we have done the spray dried processed also. So not going in a detail, all the papers we have published in details corresponding to that. So this is related to the waste plastic. Earlier we are talking about it is a graphene. Now we realize it is not the pure graphene. It is up to the
Please
780.
conclude, please.
Yeah. So these are the cell fabrication results published very well. Coming to the last slide that we have focuses. So recently we have worked on corresponding to the asymmetric supercapacitive electrode material with the Zn electrochemical deposited on the electrode. We could able to enhance from the 277 to the 341 farad per gram. So how we can tune our own material, that is important to study. and some work related to the magazine involvement also. So magazine related to the nanocarbon, as we enhances our concentration of a nanocarbon, so we could able to get the more capacitance out of it. Up to the 455 we reached. And this is the overall comparison of our work. So we are at the very good stage, and the pouch cells we have fabricated, this kind of consultancy services we have used for the fabrication of a pouch cell from the IIT Chennai lab, and coin cell we are having in our lab facility. And when we are comparing our work with the national status, so there is a SPL technology, so SPL technology private limited, which works corresponding to another, those who are working on a supercapacitors and waste polarization, these are the main companies that we are dealing with, and we are able to get very good capacitive. And with the BETEX we are in a term of like technology transfer for this carbon nanotube, and this Ganda full activated carbon for the fabrication of the battery electrodes, and some work we have done for the utilization of such kind of a biomass and related graphene out of it for the water spreading also. So here we are photoelectric water splitting. This is our very recent work that we have utilizing such kind of a reduced graphene oxide out of what the material we have proposed. So good release of the hydrogen out of it. So here when it is light off and when we'll see the light is on, we'll be having a very good amount of the hydrogen releasing out of it. So what you can see here, the big bubbles at the another electrode, these are the oxygen bubbles, and here when the kind of the redox cycle will come up to that, will be having a release good amount of the hydrogen out of it. We had measured it through the GC also, and work is well published in this, recently published in this. So all work is done in my lab only.
Sumanji, please conclude.
Yeah. So these are the recent publication and patent, and I'm very grateful to my supervisor, Professor Kumar, and who made me to be like I could able to stand before you. And these are all my collaborations to the like foreign collaboration to the different research labs. And I'm very grateful for the number of the grants I'm having in my lab from the different funding agencies, from ministries to the DSTs and all that. And recently we are getting such good grants, so we could able to facilitate some kind of in-house that is our dream center could be able to work in the near future, and happy to collaborate with all of you. Any question, please?
We do not have much time, but we can take one question. Only one question we can take. If so, there is no question. I have one query, Sumanji.
Yes.
You mentioned in Genda extract that there are some nitrogen compounds, but the compounds which you shown there were no nitrogen.
So within the lignin, so basically these are the like one you are having a branch, and one is you are having a petals. So in the petals we are having the lignin back component with the nitrogen also.
I think use extracted compounds.
Yeah, extracted out of the using the
Those
ethanol
extracted
extracted.
compounds are free of nitrogen. Eh?
No. Using the ethanol extraction we did it.
Okay, thank you. So I. Next, we have oral presentation from Sweety Chauhan. The topic is thermally stable and highly efficient tin-based perovskite solar cells with antimony sulfide whole transport layer. I invite Sweety Chauhan for the presentation.
सर स्लाइड से हो गए इससे आगे पीछे और पॉइंटर पॉइंटर कौन सा वाला है पॉइंटर का ये ओके थैंक यू ओके A very good morning, everyone. I am Sweety, research scholar from the Department of Applied Science Physics at NIT Delhi. Currently, I am doing my PhD under the supervision of Dr. Anuj Kumar Sharma and co-supervisor Dr. Nitin Singh Singha. So today, I will be presenting my work on the topic thermally stable and highly efficient tin-based perovskite solar cell with Sb2S3 as a whole transport layer. It is not working. Sir, it is not working.
आप मुझे बता दीजिएगा मैं वहाँ से
Okay. So this is the content list which I have covered during my presentation. So first I will be discuss about the introduction of the solar cell. Then I will be discuss about my simulated design. So this is the solar cell. As we already know that solar cell is a device that convert the light energy into electrical energy by photovoltaic effect. Photovoltaic effect is just a generation of the voltage due to the photon. By using this principle, solar cell works. So that's why this solar cell is also called as a photovoltaic cell. If we talk about the basic structure of the solar cell, so they are mainly the three layers are presents, main functional layer. First is absorber layer, which is absorb the light and generate the electron hole pair. Second is carrier character layers, which are basically electron transport layer and the hole transport layer, which extract the charge carrier from the absorber layer and then transport towards the end terminal of the device. And then metal contact. Metal contact is nothing but the electrode at the end of the device for the electrical conduction. Here is also given some material example which can be used for the formation of these layers. So now the question is that how we can analyze the performance of the solar cell. So there are basically the four parameters are available. Four photovoltaics parameters are available from which we can identify the performance of solar cell. So first is the open circuit voltage, second short circuit current, third is fill factor and fourth is power conversion efficiency. So to understand these parameters, we should know about the IV curve of the solar cell. So we need to look at the IV curve of the solar cell. In the curve, we can see that the VOC is the maximum point or the maximum voltage in the device when there is no load is present, or we can say that when there is no current is present. And the short circuit current is the maximum current in the device when the circuit is short. And the fill factor is basically describe or basically compare the performance of the solar cell with the ideal solar cell characteristics, and it can also calculated by equation 1. And the power conversion efficiency basically describe the ability of the solar cell, how much the light is convert into electrical light is converted to the electrical energy, and it is calculated by the equation second. Now next we talk about the different generation of the solar cell. So on the basis of material, we have a fourth generation, in which the first generation is totally described by the crystalline silicon material, which provide the higher efficiency, approximately 26%. But due to the higher cost, the second generation was developed, in which the thin film solar cell was developed, in which CIGS material, amorphous material and CDT materials are used, but they shows the low efficiency as comparable to the first generation of solar cell. That's why the third generation was developed, in which the new type of materials are used, such as the perovskite material, which provide the higher efficiency, which is comparable to the silicon based solar cells. But the drawback is that they have some stability issue. So now the research is ongoing to enhance the stability of the perovskite based solar cell. So on base of these perspectives, my topic is thermally stable and highly efficient in base perovskite solar cell with Sb2S3 as a whole transport layer. Sir, it is not working. Back. No, thanks. No, back, sir. Thanks. So this is the simulated design structure. Basically, in the perovskite material, we use the organic hole transport layer, such as the spire-omnited hole transport layer, but they have some drawback, like a stability issue when they exposed to the moisture. So there is a need to find the alternative of spire-omnited material. So here I have used the Sb2S3 material in place of spiro-omnited material, and the STO is a electron transport layer, and the tin based perovskite material is used as an absorber layer. So these are some parameters of layer which I have used during my simulation. So let's start with the result and discussion portion. In the result and discussion, my task is to analyze the thermal stability by varying the temperature. Why this is important? Because the temperature variation is crucial to understand the stability, efficiency losses and the real world performance of the solar cell. For example, if we use a solar cell in the Delhi, is this possible that the same solar cell will give the same performance in the hotter region places? No, it is not possible. So that's why the analysis of the temperature is also important. Sir, further. So here is the JV characteristics of the proposed design. This JV curve is plotted under the variation of temperature ranging from 290 to the 330 Kelvin. And from this graph, I have analyzed that the magnitude of the JC is almost stable up to 0.9 volt, but the VOC decreases as the temperature increases. This is happened because of the higher recombination. As the temperature increases, the band gap of the material will decrease, and which is responsible for the recombination. But this reduction in VOC is minimum. As we can see that in 290 Kelvin temperature, it is almost 1.21, and 330 Kelvin temperature, it is 1.81. It is almost 2 to 3% decrement. Next. Next is the JSC variation under the coupled effect of the absorber thickness and the temperature. From this graph, I have found the best combination of the thickness and the temperature, from which I get the higher value of the JSC. So the highest value of the JSC is observed for the thick absorber layer around 900 to the 1000 nanometer thickness, and as we already know that the JSC is minimum affected by the temperature. Further. So similarly, the PCE variation, in the PCE variation we observe that for the design we obtain the highest PCE at the 1000 nanometer thickness of absorber layer and under the low temperature 290 Kelvin, which is 36.39% PCE for this design. I have also calculated the power temperature coefficient for this design. It is minus 0. Okay. So the power temperature coefficient value for this design is minus 0.017% per Kelvin, which is very lower, which is very low than the silicon based solar cell. Power temperature coefficient is basically described that when we increase the temperature 1 Kelvin, then how much the performance will change. So for this design, it is changes 0.0117% Kelvin. Further. So here is the comparison table in which I have compared my design with the current state of art, and I have found that this design shows the highest power conversion efficiency and the higher thermal stability as compared to the other design. So in the conclusion, the proposed design exhibit the highest value of the PV, that is JSC is around 33.16 milliampere per centimeter square, and the power conversion efficiency is 36% at a 1000 nanometer thickness of absorber layer under 290 Kelvin temperature. And this design also exhibit the higher thermal stability within the temperature range 290 to the 330 Kelvin. And the power temperature coefficient value for this design is minus 0.017% per Kelvin. So we can say that this design shows the higher thermal stability and higher performance as compared to the other design which is present. So these are the references. So in the last, in the acknowledgement, I would like to thank you to the NIT Delhi and Director of the NIT Delhi, Professor Ajay Kumar Sharma, and biggest thanks to my supervisor and the co-supervisor, Dr. Anuj Kumar Sharma and the Nitin Singh Singha. Thank you so much.
Are there any question now?
Which method you have used to synthesize your material?
What?
Which method you have used to synthesize your material?
This is the simulation part. If we want to synthesize this design, so there are many methods are available. For example, the spin coated methods or the three-step evaporation method, which is very beneficial to design the stable solars.
Yeah.
Yes, sir.
Definitely you are showing a single cell.
Yes. Yes, sir. Yes, sir.
That is 33%. Single cell cannot have efficiency more than 30%.
But sir, recently there are many papers are available who reported the efficiencies.
Any of the experimental papers.
No, simulation papers, sir.
Believe on the simulation so much that whatever you are representing, that should be within the limit also. You
Yes.
cannot go beyond the limit.
Okay, sir.
Okay, so cross verify your results.
Okay,
And the mistake I can tell you.
You.
So how you have taken care of absorption in this case? Is it self-driven by the SCAP software, or you have taken from experimental?
Sir,
Have you taken experimental absorption spectra to produce the?
no, sir. SCAP software.
Then this is the mistake. Fine. So
Okay.
you have to refine your results with the help of that.
Okay, thank you so
These
much,
are
sir.
two my suggestions.
Thank you so much.
Any more question? Okay, no question. Then we'll break for the tea for 10 minutes and then we'll come back. Thanks very much.
Thank you so much.
University, and he did BSc, MSc from Kurukshetra University, PhD from the Roorkee University, and he did postdoctor from this Iowa State University. And he is the gold medalist, Times gold medalist in BSc and MSc. And he has international collaboration in USA and Europe. And he has published more than 110 scientific research papers in international journal. And he has this life member of the board of this Indian Science. And he has produced 9 PhD students and 6 PhD students are working with him. And he has 3 projects supported by this EGC, DST, and SUB. And I request Professor Mahesh Kumar to deliver his talk.
Hello. Okay, thank you, Professor Adreja ji, for the introduction, and sincere thank to the all organizer, especially Professor Malik and Dr. Neeraj, for inviting me to deliver a talk on my research area, one of the research area, that is on perovskite solar cell. Okay, so we do theory as well as experiment in this particular area, and the one scenario of the perovskite solar cell which I will touch in this presentation is triple cation based modification in the absorber layer of perovskite solar cell. So in this talk I will touch sustainable energy, what is the need, generation of perovskite solar cell, the comparison between perovskite and the silicon solar cell, fabrication simulation of perovskite solar cell from our group, and the future aspect conclusion. So, if we talk about this sustainable energy, current global power demand is 24 terahertz per hour, and by 2040 it will increase by 37 terahertz per hour. Okay, so burning by just fossil fuel, so you cannot achieve this amount of the energy, and you need the renewable energy resources. And if we talk about the research in the laboratory, so you can focus on photovoltaic material, thermoelectric material, and piezoelectric material to give some contribution in this renewable energy resources. So this is a particular graph which shows that India is having a dire need of renewable resources, because this is the yellow is for India, and from 2000 to 2040. So see, so our energy demand is going to be increased, and USA is already established, so they are having these complete demand and supply chain for the energy, whether it is 2000 or 2040. And among the power installed capacity of by sources in the various countries, so you can just in our country, so you can just say that in 2040 solar PV will lead as compared to other ones. So currently the non-renewable resources are dominating definitely, but solar energy will be the very first target in 2035. Now, why this solar energy is so much important? Just you can have a comparison that every hour sunlight from the sun is coming on the earth, and it can meet the demand of power for the entire world for 1 year. How? So the amount of energy which is reaching on the sun, which is reaching on the earth, is 4 × 10⁻18 joule annually. And if we talk about the annual consumption in the world, so it is 3 × 10⁻14 joule. So it is much more higher as compared to the demand. So if we can harvest some of the energy, so if we can accomplish the demand. But So what is the benefit of using the solar energy? So you can say that there is no environmental concern, no reduced carbon emission, no pollution in the harvesting, and you can save the money on the electricity bill. And definitely each and every day's new technologies are coming into the picture, which is giving the better and better performance for the solar cells. So people are having the interest in this one area, and you can increase the home value also. So solar cell is a photovoltaic device which converts light energy into electrical energy, and based on the photovoltaic effect, that is photogeneration of the charge carrier in a light absorbing material as the result of absorption of photons or light radiation. So the property which are mainly on of the focus is open circuit voltage, short circuit current density, fill factor, and based upon that you can calculate the power conversion efficiency. And there are some factors which can deteriorate the performance of a solar cell, that is the light intensity, what type of light is coming, what is the color of the light, what is the angle of the incident light, and what is the surface condition of the solar cell or solar panel, so whether it is clean, dirty or not, and what is the temperature of the solar cell. So based upon the various discovery of these solar cells, so we can divide the solar cell into 4 categories: first generation, second generation, third generation, fourth generation. And the first generation we are having the silicon based solar cell, and the second one it is thin film based solar cell like CIGS, CDT, CDS, and so on. And in third generation we have dye synthesized solar cell, quantum dot solar cell, organic solar cell, perovskite solar cell, and so on. And in the fourth one we are having the hybrid ones, and metal nanoparticle and metal oxide based solar cell. So if you are working in this particular area, so you must be seeing this particular chart maybe I think weekly, and this chart is being changed as per the new discovery. So if you just see, so this is the line for perovskite solar cell, and for silicon solar cell it is this line. So for silicon solar cell single crystal, if I talk, so this is the line. So you can just imagine for silicon solar cell and perovskite solar cell, both are having almost similar type of the efficiency, that is 27%. And perovskite solar cell have achieved this efficiency within 15 years, and silicon solar cell have taken more than 50 years to get this particular amount of the efficiency. So means there is a steep growth in the perovskite solar cell. So now the question comes, what is this perovskite solar cell? So you can say that any material in which the absorber layer is made up of perovskite material is called perovskite solar cell. For example, we are having this particular formula for the perovskite, that is AbX3. A and B are cation and X is anion. So A can be a combination of two different cation also, so it may be a combination of organic and inorganic cation, and B is a metal cation like PbS and Ge, and X is the halogen ion. So if this A is mix up of organic and inorganic one, so then you can say that you are having organometallic halide perovskite material. So any material so in which solar cell is having the absorber layer made up of perovskite, so it is called perovskite solar cell. So why it is so much important? Because perovskite is having the tunable band gap, and it is having high carrier density. So low diffusion length for the charge carrier, high absorption coefficient, and you can produce these solar cell by a simple fabrication method in the laboratory. And see here, so efficiency has grown within a 15 years from 3.8% to 27%. So all these are the properties for a good photovoltaic material. Now the question is, if I am praising so much about the perovskite solar cells, so where is the problem? So problem is lying in this particular diagram. So if we start from C, so see here, so efficiency is at par. So there is no problem in the efficiency for perovskite solar cell and the silicon solar cell. But if we talk about the cost, so in the cost, perovskite solar cell is winning over the silicon solar cell, and it is the low cost fabrication. But as soon as we come to the A part, so this is the stability or lifetime. So lifetime of perovskite solar cell is very much small as compared to silicon solar cell. So that's why, so this is the main hurdle. So means we have to increase the stability or lifetime of the perovskite material so that it can be used for the solar cell application for a long time. Fine. So, so if this hurdle has been crossed, so then this perovskite solar cell will take the place in the market from silicon solar cell. So this is the main structure or layer by layer growth of perovskite solar cell. So you are having glass substrate or FTO substrate, and then TI, that is electron transport layers, and then you are having the main perovskite layer in which the absorption of the light take place. So all these are the transparent layers. So light can go up to the absorber layer, and here the electron and hole pair get converted, and after that, so if electron and hole pair are separated here, so electron will go in the electron transport layer and hole will go in the hole transport layer, and from the external circuitry, so we can have a potential difference. You can have the electricity in this way, and then finally you are having the metal contact from where you take these charge carrier outside. Now the question comes that how to make these perovskite solar cell in the laboratory. So, these are the main steps for the device fabrication of the perovskite solar cells. So first you have to do the substrate cutting and take the conducting substrate, that is FTO or ITO. You can do the patroning, you can go for the masking as well as etching, and then you can prepare the substrate by the cleaning. After that, synthesis of the precursor solution. So precursor solution you can easily make in your laboratory. After that, so you have to go for the spin coating. So this should be done at least in the glove box or in the clean room. And so with the help of spin coating, so you can go, grow layer by layer growth of these ones. That is ETL, STL, and absorber layer. Finally, you can make a contacts with the help of metal contact, with the help of this thermal evaporator. And you can have the efficiency measurement with the help of solar simulator by just plotting this IV plot. So this is the main diagram. So you can say that is substrate cuttings, and so after that you can have the masking so that you can make the front as well as back contact of the metal, and then you can apply the zinc dust and put some drops of SCl to make it more clean and visible. And after the etching, so you can have this patternized substrate. Okay, so this is a substrate. So after the patterning with the Kapton tape, it will look like this, and then you apply this one, that is zinc dust and SCl. So after the etching, so this is the patternized substrate. So if you have the patternized substrates, you can apply the tape for the front contact also, because you have to make the front contact also. Two contact you need for the metal, that is back contact and front contact. So this after this tape, so you can go for the growing ETL, absorber, and HTL subsequently by the spin coating method. So 1 layer, 2 layer, 3 layers, and then deposition of the metal back metal contact with the help of thermal evaporator you can do. So in this way you can have a final device, and this device is ready for the measurement of the frequency. So first step involves solid state synthesis, thermal thin film deposition, and then metal contact with the help of the thermal evaporation, and finally the characterization. So this is the fabricated perovskite solar cell device which looks like so, and when you place this particular device, so it should be black in color. Fine. So if it is moisture free, it will be black in color. And whenever you will put this one in the under the solar simulator, so it will illuminate, and so you can have the IV measurement with the help of that. Now, so I am just trying to show you that how we do this particular experiment, and how we tailor this particular layer, that is the absorber layer, perovskite layer. So as I said, as per the title of my talk, so we have to do the engineering of this A material, means A, B, X3 you are having. So for A you are having 3 cations, that is Fa, Ga, and Cs. Okay, so for this X we have changed the doping concentration, and now what is the problem in one particular cation? Suppose you are having Fa or Ma, and both are the organic cations. So in Ma, so MaPBi3 is having less thermal stability, and FAPBI is having the thermal stability more, but still it is having issues with the moisture. It is having the problem of the non-perovskite phase, that is called delta phase at the room temperature, which is not photoactive. So means directly you cannot use FAPBI3 or MAPBI3, or you have to do the engineering of this particular cation, that is FA or MA. So we have tried with the FA, so that's why I am showing you the result for the 3 cations. So first of all, so it is important to check whether whatever the material you are designing, even if you have taken the 3 cations, so it is the having the perovskite phase or not. So it can be checked with the help of tolerance factor, and if tolerance factor is coming in between 0.8 to 1, so it is the perovskite phase. So for all the samples, so it is coming more than 0.9, so this means it is a perovskite phase. Then you can check the XRD pattern. So for all the ions, so all the samples, so this is the reference sample, 1% doping, 3%, 5% and 10%. So as we go from 1 to 10%, so what we see that in 10% sample, we are having a formation of delta phase. And so this is not non-perovskite phase. So means it is not a suitable sample, but all other can be a suitable sample. So now, so as we have made these 4 samples, so out of this 3 may be a suitable one. So out of these 3, so which one is having the efficiency more? So for this we have done the another characterization. So first of all, the band gap measurement. So for the band gap measurement, so you should have optimum band gap. So optimum band gap is 1.5. So all the material is having the band gap 1.5, near to 1.5. Even we have checked not only from the UV visible, but we have checked from the photoluminescence also. And if you just check the difference between these two, determined from the UV and PL, the difference is very small. That is called the Stokes shift. So Stokes shift is very small, and Urbach energy is also coming in the milli electron volt range. So that's why you can have the stability of these particular material. The grain size coming from the FESM is near to 200 nanometer for all the samples. So this means you are having the nearby thickness you can monitor in this way. Now, so how we can do the similar type of the thing from theory side? Fine. So this is our FAPBI3. As I said that it is having the problem with the moisture, so we have to do the engineering of this one. So first we have to introduce the second ion. So second ion is this cesium. So cesium and the cesium you need suppose 16 or 17%. So for this you have to make the supercell of this one, that is 3 to 1. So when you will do 3 to 1, so 3 means in the x direction you have to take 3, and in y 2 unit cell, and in the z it is 1. So if we just try to check the this particular center one, that is the FA cation. So one of the FA cation is replaced by the CS1, and if we just try to check the dopants concentration, it is coming out to be 17%. So in this way we can make our pristine materials. After that you can have the third cation introduction. So this the analysis of this one can be done from DFT calculations, and suppose this is the total dose. So in the total dose, which states are contributing, and in the vicinity of EF, suppose this is the EF, so clearly it is a semiconductor one coming out one, and in the vicinity which states are responsible. For example, if we just talk about this PB state, so it is having the more contribution in the conduction band, highlighting its vital role. And in the valence band, so you can have the SP orbital, so which is mainly contributing, and the same way you can check the contribution of FS and CS and FA ions. And finally you can say that this is FA ion, so it is far away, you can say, and so it is barely contributing the dose in the vicinity of EF, and suggesting that organic cation exhibit the minimum direct impact on the electronic state of near the band edge. You can check whether it is a direct band gap material or not with the help of this band structure calculation. So along the RR directions, so you are having a gap that is 1.5 to 542 electron volt, and the experimental value is 1.547. Okay, so this is from the DFT calculation. Now, so it is also important that after the doping, you should have the live charge carrier lifetime should be increased. So carrier lifetime is being increased from 17 to 20% after the 3% doping of gunidinium cation. And so this is the complete you can say TRPL imaging in which the average lifetime has been shown. So finally you can go for the efficiency measurement. So as direct exposure of sun, we are having a replica of this one with the help of solar simulator. So under the solar simulator, you can go for the reverse as well as backward scan. So generally we take the reading from the reverse scan, and for 3% doping, so it is 20.7 efficiency is coming, and for other ones, so it is slightly less. So this means, so this is the required combination in which we should select. And it is also important. So whenever you are claiming you are having an efficiency for a particular solar cell, so you should repeat that particular experiment and you should get the same result. So we have done so. So we have tried to check the efficiency for 20 devices. See the statistical distribution is, for example, if I talk about, because this is my champion device, that is 3%. So VOC, JAC and fill factor and this efficiency. So for all the 20 devices, the statistical variation is very small. So this means if I am having this particular plot, I am ready to say in my paper or manuscript that this is my efficiency. Otherwise, if you are not producing the same efficiency for example, a multiple number of devices, so this means you may be wrong. So this is the bar diagram that how the film is being degraded. So after 3000 hours, so you can see that in comparison of the reference material, so if we have 3% gunidinium one sample, so it is degrading less as compared to the reference one. Now the second one we have done in this case, K, CS and FA triple cation combination we have taken, and this time we have focused mainly on the absorber layer, that is the perovskite absorber layer consisting of these three cations. So the procedure is same, that you can have the mixing of the salts and you can heat, you can make the FA, iodide of FA in this way. So this iodide of FA with the other iodide, that is PB and CS, you can mix up in the according to stoichiometric combination with Ki. So you can make a precursor solution for this one. So this is the precursor solution for our absorber layer, which is having the three cations. So after the coating of the this particular precursor solution on the with the help of spin coating, so you can anneal the sample and finally you can obtain the film. So this film should also be tested. Not only the device, but film should also be tested. And so if we just try to check, so we are having the three combination of K, that is 3%, 5% and 10%, and so, and this is without K, and this is our pristine one. So if we could try to compare these 5 so you can just see the delta phase is there for FA, and because it is the non-perovskite phase, but as soon as we are going to add the second cation or the third cation, so this delta phase is being removed. You can just check, and finally for the triple cation combination, so delta phase is not there. You can check with the help of SEM images what is the size of your crystals. So you can have the 239, 351, 222 and 305 nanometer is the particle size coming from this SEM analysis. So you can go for the band gap analysis, and the band gap for all the samples, that is 3%, 5%, 10%, and for the double cation also, so it is having a optimum band gap, that is 1.5 electron volt. You can check this photoluminescence spectra and absorption S you can try to find. So absorption S is also having the same corresponding band gap or wavelength is the same for the band gap. So this is shown here. So from the UV visible, from the photoluminescence, you are having this particular band gap, and Urbach energy is also coming in the milli-electron volt. So finally, so this is again the charge carrier lifetime. So you can just check that as compared to double cation. So we are having 3 cations, so in which this 10% is the non-perovskite phase, but these two are the perovskite phase. So see, for the 3% and the 5%, the charge carrier is large as compared to the double cation one. And you can measure this lifetime, average lifetime with the help of corresponding the sample one. So for this one, so for 5% case, so average lifetime is the maximum one. Now, so this part we have done for this particular sample, we have done this part from theory side, that is the device modeling with the help of SCAPS, and the efficiency is coming for the 3% one is the maximum one, and here we have used the absorption spectra from the experimentally measured sample. So if we take the SCAPS simple one, the from the data of the SCAPS, so this efficiency will come out to be very large. So that is wrong, but so we can, if we are taking this the absorption spectra in the SCAPS calculation from the experiment, so the efficiency is reliable. Finally, one more case, so I'm showing you. So this time, so we have tried to check the A cation engineering for FACS, and this time, so we have tried to compare not only K, but instead of K, we are having GA and MA. So what is the difference between these? So this is our the pristine material, and the third cation we have taken the different one, that is K, GA and MA. So procedure is again same, that is with the help of spin coating you can achieve the perovskite thin film, and then with the help of XRD you can just check whether you are having the formation of delta phase or not. So delta phase is coming for this particular one only, and but for other two, that is no delta phase is coming, and the cubic phase of perovskite is having these particular Miller indices, and all these Miller indices are present in these samples. And the crystallite size you can just check, so it is coming out to be 94, 120, 122, 92 and 105 nanometer from the XRD analysis. Going for the UV visible spectra, so again you are having for all the sample, the band gap is 1.5 electron volt, and high absorption is expected, you can just say, and accordingly you are having the high thickness. So out of this if third cation is MA, so it is showing the highest absorption, whereas for the if third cation is GA, then it is having the lowest absorption. And CS content, if we try to increase from this to this, so CS content is increasing, and it is giving us the better absorption, and the band gap value is increasing slightly, but still it is near to 1.5 electron volt. So you can say that under the ambient environment, it is important to check the stability, because you can make this perovskite solar cell, but on the next day your perovskite film may be degraded. If perovskite film is degraded, so this means you will not achieve any efficiency from that. So for this one, so stability analysis is more important. So we try to check the stability analysis for 90 hours, that how the film is being degraded. So you can say that all the sample are degrading under the ambient condition, because generally whenever we prepare the perovskite solar cell, we keep it in the glove box or in any desiccator or whatever it is, means where the ambient environment is not there. Fine. So but out of these films, so you can say that in where we are having the third cation as K, it is showing the less stability, and where we are having the MA as the third cation, it is showing the highest stability. So it is clear from the thermoluminescence spectra, photoluminescence spectra also. So we can have the for this one, the absorption edge is having the maximum intensity, that is the MA, CS and FA case, whereas the other three are having not significant one. And then you can just check what is the IV characteristics from the help of solar simulator, and the efficiency for all these three cases are in this way, that is KCS FA is having the maximum efficiency, that is 18.17, wherever the stable one is having the 19.07%. So this can be done with the help of solar simulator, and So it is mainly the tuning of these three cations which can play an important role not only in the efficiency measurement but also in the stability. So this is the efficiency degradation. So we try to compare from day 1 to day 5. So 0.5 degradation, 5% degradation, 1% degradation in this sample, 1.5% degradation in this sample. And you can have the similar trend from the reverse scan also. So means you are having the maximum degradation in this one and the minimum one in this one. So what is the message which we can take? So this is my coming to the last slides only. So this type of research we can do in experimental lab and theoretical lab. So we can target 4 type of the different research. So in the wet lab means in actual experimental lab. So you can go for the material synthesis. Like the second work I have shown you, that is focused only on the perovskite material, right? So means we have target the perovskite thin film. Whereas you can go for the complete device also. You can grow the complete solar cell and do the efficiency measurements. Okay, so for this one you need the thermal evaporator as well as the solar simulator. But these days people are also focusing on the dry lab, means simulations, because simulation are also giving you the better result and these are comparable to the experimental one. And for this you can go for the DFT modeling of the materials, and we have certain device modeling software, and these are modifying their parameters in such a way that the results are reliable now. So you can have SCAPS, FORSET and COMSOL multiphysics. So certain software these are, so where you can go for the device modeling also. So this is the future aspect, that if we have to go for the fabrication of these solar cells for the low cost basis and high efficiency we should expect, so that we can use it for the industrial developed product and make it available for the common people of the rural India at the affordable prices. So these should be developed at the small scale need. And if we can develop these ones, so rural people can take the benefit where the light is having the main problem. Small scale industry of the perovskite solar cell will boom within next 5 to 7 years, and this will be a revolutionary step for the next generation solar cell and also for the industrialist. So finally the conclusion, so we can say that solar cell and solar energy is the future of next generation solar cell, and perovskite solar cell are flexible, cheaper and recycle. Flexible means it can be applied any surface. Cheaper means it can be produced at the low cost, and recycle definitely. So this is based upon the material like carbon or hydrogen, oxygen. So this can be recycled easily as compared to silicon solar cell. So triple cation in the perovskite structure not only enhance the stability but also the stability, not only enhance the efficiency but also the stability of these perovskite solar cell. And by the end of 2035, so you will have a dominant share of perovskite solar cell having the efficiency over 30%. Definitely for single cell it cannot go 33%, right? And thanks for your kind attention. So this is end of my talk.
Thank you very much for the crystal clear talk and very interesting talk. Now it's open for the questions. Any question?
Nice talk by you.
Thank you.
I just want to know that degradation is one of the main problem in these types of solar cells. How can we overcome this problem?
Well, one way I have just suggested you that you can go for the triple cation engineering. So that's what we are focusing these days. And these are 3 layers. Fine. One is the ETL absorber layer and the HTL, that is whole transport layer. The main problem is coming from the absorber layer. Okay. And people are now trying to add one buffer layer also, so that the surface of the perovskite material can be protected. And this can also be one of the solution. That is using
I think encapsulation is one of the.
You are right. Encapsulation can also be a solution.
Another question. I think contact is one of the crucial part in this type of solar cells. By treating them with plasma,
some groups treated them with plasma and they got some increase in their efficiency.
Yes.
Have you tried this?
No, we have not done it in the plasma environment. So it is simply with the help of thermal evaporator. By just making the front and the back electrodes with the help of thermal evaporator.
So you use ITO and gold.
ITO and FTO.
ITO as an anode and which types of electrodes, which two types of electrodes you are using?
Generally
ITO
and gold also.
Gold also.
Gold, yes.
Okay. Both have similar work functions.
Yes, it is
nearly same.
Near similar. Yes.
4.2 EV, I think. 4.1.
I hope so. I have not checked this one.
Okay. Thanks.
Okay, thanks, Professor Kumar. Next talk is the invited talk by Dr. Anurag Gaur. He receives PhD from the IIT Roorkee and present work is the Associate Professor in Department of Physics, Netaji Subhas University of Technology, New Delhi. Before he joined this university, Dr. Kaur served at the National Institute of Technology, Kurukshetra for 14 years. Dr. has been research work on the functional nanomaterials, energy storage devices, spintronic. He has published more than 150 research papers in international journals. And he was awarded the Young Scientist Research Project by the Department of Science and Technology, Government of India. And he was he has supervised 8 PhD students, 70 MTech theses, and 5 patents are also there. He has more than 4,400 citations. H index is 37, I index is 10, and Dr. Kaur is the editor of the Applied Science Letter and reviewer of the various international journals. And I invite Dr. Kaur to present his work. So you got 25 minutes plus 5 minutes.
So thank you so much, especially for introducing myself by the chairman of this session, and also the organizers who give me the opportunity to interact with the participants of this conference. So as you can see, the title of this talk is Fundamentals and Fabrication of Supercapacitors. Fundamentals I will just review, especially for the students, if someone want to work in this area. So they can just understand that what are the important fundamentals involved in the field of supercapacitors. So there was also one talk before to me in the earlier session on the supercapacitors. So I will just focus on those particular points that you can understand something and you can have some idea that how these supercapacitors works, as well as what are the fabrication methods and how we can fabricate these supercapacitors. So the first thing is that why we need the capacitors or supercapacitors. You know that we already have the capacitors, but their capacitance is very low So actually that this purpose of the supercapacitor is that we have to enhance the capacitance of the capacitors. And we are looking about the capacitors as an equivalent device that can, I am not using the word that they will replace the batteries, but they should be competent and equivalent to the batteries. So that is the purpose. But what is the, if we can compare the benefits, like why we are talking about the supercapacitors, what are the advantages, that is important. So even in the current scenario, if we can compare their energy density, so that battery has the advantage. They have the higher energy density, but the power density is large in case of the capacitors. So you can understand that power density means if we have to release the power instantly, then you need high power density. But if the stored amount of energy has to be released in the longer duration, so then you need the higher energy density. So especially for the storage device, we want that the charging time should be large, so energy density should be large. But what is the major advantage if we can switch toward the supercapacitors? That is the life. Because if you compare the battery life, it is around 3 to 4 years or 4 to 5 years, because battery depends upon that how many cycles the battery can run. So especially 3 to 5,000 cycles battery can run, because there are electrochemical reactions. The redox reactions occurs in the batteries, while in capacitors the redox reaction does not occur. The charge storage is electrostatic. So because of that their life is very large, 20 years, 30 years. So idea is that if we can make the energy density of the supercapacitors equivalent to the battery, so then they will be better alternate, because life is 20 years. And if we have the similar amount of the energy density, so that will be a very good alternate. So that is the idea about these supercapacitors. So but thing is that I will not go about this, because you already understand that battery have the high energy density and the capacitors have the high power density. So this gap is being fulfilled by the electrochemical capacitors. So you have learned about the word supercapacitor. So basically they are electrochemical capacitors. So what is difference in comparison to the normal capacitor? So in normal capacitor you have the two metal plates, in between there may be some dielectric materials. So these are conventional capacitors, but their capacitance is very low. It is in microfarad and in that range. So supercapacitors we are replacing, there is that we are using the electrolyte in between the electrodes, and because of that their capacitance become very large. It was in microfarad if it is in conventional capacitors, but in supercapacitors it will be 100 farad, it will be even 500 farads. So that is the idea that people are working in this area of the supercapacitors. So how the capacitance increases, because the energy densities depend upon the capacitance. You know the formula E is equal to half CV square. So we have to enhance the capacitance. So to the what is the capacitance? Fundamentally you know that C is equal to epsilon A upon D. It was the formula is being decided how the capacitance depends. So it is depending upon the area of the plate, and D, this is the distance between the plates. So as much as the area of the plates will be large and distance between the plate will be smaller, the capacitance will be large. So similar thing is being done with these electrochemical capacitors, means the supercapacitors. So first thing is that we have to make the electrodes, they can have the high surface area. That is the very important things if you want to enhance the capacitance. So as a being material scientist, you must have the expertise in the material fabrication, that how we can make the materials with the large surface area. And second thing is that D value is very smaller. It is of the order of angstrom or nanometric level in case of the supercapacitors. So because of that they have the large capacitance. I just tell you to brief that how this C is so smaller. So this is smaller because of that. It is a working of a EDLC based electrochemical means pseudo. This is the capacitors where it is called the EDLC, means the electric double layer capacitor. So what does it mean? There is a double layer, but the charge storage is purely electrostatic, as in case of the conventional capacitors. And the D value is so smaller because this is your one of the electrode. We are using here the carbon as a one electrode, and both of side is the carbon as electrode, and electrolyte in between is there. So once we charge in the charging process, so this is the positive terminal, so negative ion of the electrolyte, they will come to this positive side, and this positive ion to the negative side. So there one capacitor is developed itself at the interface of your electrode. This is your electrode ion, this is the electrolyte ion. So the distance between these two, it is of the order of angstrom level. So because of that, the capacitance is large, and we can have here the two layers are formed, means two supercapacitors are formed. So because of that, they are called double layer, and we use a separator in between them that could avoid the short circuiting, and this separator is a porous material that could allow ions to move from one electrode side to the another electrode sides. So that is the things about these supercapacitors. But basically these are of two types. In the supercapacitors, there are two categories. One category is the electric double layer capacitors, and another is the pseudo capacitors. So electric double layer capacitors, they are purely charge storage phenomena is the electrostatic, as in the conventional capacitors. While in case of the pseudo, as the name itself indicating, they are not actual capacitors. So the charge storage phenomena is mixed in case of pseudo capacitors, means there will be electrostatic charge storage as well as to the electrochemical. So because of that, they are calling the pseudo capacitors. So the play is only between that what you want, whether you want high energy density or whether you want to high life of the device. So if you want that the life of the device should be long, so in that case you have to be dependent only into the electrostatic process, and you have to go for the electric double layer capacitor. Their life is very large, 20 years, 30 years. But if you also improve the energy density, then you have to go for the pseudo capacitors, or either we can call them the hybrid supercapacitors. So basically electric double layer capacitors, their both electrode are of carbon based, because you know that carbon, in case of the carbon, no redox reactions occurs. So you can use the carbon as a electrode materials. So there will be the electrostatic charge storage phenomena, but if you take the metal oxide, then redox reactions occurs, and because of that the charge phenomena is mixed. There will be at the surface there will be electrostatic, but also the electrochemical reactions take place, and that could take part in the capacitance process. So these are the, if your electrode is metal oxide, so then there will be pseudo capacitors. If they are only the carbon based, they are called the EDLC based electrostatic capacitors. Hybrid means that you can also play in between these two. You can take one electrode of carbon based and another electrode you can take the metal oxides. So in that case you can make a good device which can have the significantly high value of the energy density as well as to the life. So these are about the details that how the supercapacitors are working. I am not going into detail of that, but one thing is very important to understand, that suppose you make some supercapacitor. So whether what is the charge storage phenomena, whether they are purely electrostatic, whether they are the pseudo capacitors, or whether they are the battery type, because sometimes you will get the comments that you are talking about the redox reaction, so why they are not the batteries, why you are calling them the capacitors or pseudo capacitors, why you don't call them the battery materials? So that is the fundamental things you have to understand about their CV measurement. These are the electrochemical characterizations you have to perform, and you have to see that what is the CV curve and what is the GCD curves. So that will give you the idea whether the charge storage is purely electrostatic or whether it is the mixed, means the electrostatic as well as the electrochemical, or whether they are the battery type where the charge storage is purely electrochemical. So for that, if you have this kind of the CV curve, it is in this square shape, so it is a purely electrostatic charge storage. But if you have this one which is at the extremely right, it is case of the batteries where the oxidation reduction peaks are dominating. So purely charge storage phenomena is the electrochemical in that case. So in between, this is the pseudo capacitor category. So I have classified even the pseudo capacitors in the two categories. One is there the redox reactions occurs, but they are on the surface. At the surface redox reactions occurs, and second is that where the intercalation process is dominating. So you know that intercalation is more dominant in the battery case, that how the ions they will enter in between the layers for the longer duration. So intercalation if dominant, so it means that pseudo capacitors, they are very close to the battery, they are almost like to the battery, and if they are on the redox surface reactions, so they are close to the EDLC type, electrostatic supercapacitors type. So similarly you also can see that this is the GCD curves, you can see that how this potential vary with the time. So you can realize if it is linear, it is purely electrostatic, and if it is like that, it is the battery. So that is the basic fundamental about that. We have to be think how these pseudo capacitors works. How we can fabricate them? So you see that what is the fundamental in the fabrication part. First, you will decide that what will be my electrode materials. If it is only the electrostatic double layer capacitor, so you will take the carbon as a electrode material, but if you are using pseudo capacitors, you can take the metal oxides. But important part is that once you are synthesizing these materials, you have to adopt those synthesis methods so that surface area could be large. Two things are very important in case of supercapacitors. One thing is the material surface area should be large, and second is the pore size. What is the pore size of the materials? So it must be into the nanoporous range, 2 to 50 nanometer, and surface area should be as large as possible, because in the same material you can have a very difference in the results. So because of that, it's important is what is the surface area. As I told in the starting, it's play major role into the what will be the value of the capacitance, and second is the pore size. So we have to firstly make the powder material, and you can adopt any chemical routes. They are very you see that by that you can make the large surface area materials, and after making this powder material, so then you can make the slurry. So in slurry you can mix up the PVDF and all this, the carbon black, to enhance the conducting channels in between the electrode materials, and that slurry has to be coated over some base material. So base is basically the current collector. Some people use the nickel foam, or some people use the graphite, but graphite is better, because if you are using the graphites, then there is no scope of the redox reactions contribution if you are using any electrolyte. So therefore graphite sheet you can use as a base material, and over that you have to be coat this slurry. And here the one important part is the mass loading. Mass loading means how much amount of this slurry you are coating over your graphite sheet. So that should be ideally 3 to 4 milligram per centimeter square area, because if you will deposit the large amount, then only the upper layers will be contribute for the capacitance. The bottom layers they will not contribute, but when you will divide with the weight, so then your capacitance value will be smaller. So you have to properly that you see that how much mass loading you are doing on the substrate, and accordingly you can make the different kind of the electrodes. These electrodes in that way. And if you want to make the coin cell, so coin cell, this is the final cell using 2 electrodes. So you have to firstly coat your this slurry over some base material, whether graphite sheet or some nickel foam, and then cut it as per the diameter of your cell. So this is one electrode is ready. Similarly, you can make the second electrodes. You will use these coin cells, you put one electrode, then you can have some separator and keep few drops of your electrolyte, and then put another electrode, and then we have the crimping machine, we crimp them, and finally this kind of cell is ready to use. So that is the method that how you can fabricate these supercapacitors. So initially you synthesize the materials, and then by making the slurry and coating you can finally make this kind of the device. Experimentally how you can perform that? So simply that firstly what we have to do, you have to test only the single electrode, and single electrode will be tested with this 3 electrode system, that is about the electrochemical chemistry. And once the 3 electrode system you have been checked what are the parameters of your single electrode, then you have to go for the full device. Full device means you are having 2 electrodes and in between electrolyte is being filled, and finally you are going for the testing. So in that case you will use the 2 electrode system only. So that is the, I am not going in much details because of this time limitations. So that is CV characteristics. So you can do the CV and you may get, if it is a pseudo capacitor, so that kind of CV curve you will get, and then you can calculate capacitance. So it is not the like EDLC. So here you will use this formula and you can calculate the area in this area, because integration is there, and you can calculate the capacitance value. So that is the you can find out firstly the capacitance. Another important part in case of these materials is pseudo capacitor is the contribution of the, because the mechanism of the charge storage is mixed. In case of the pseudo capacitor, charge storage will be electrostatic as well as to the electrochemical. So that is important. You have to calculate the ratio, that how much contribution of electrostatic and how much contribution of the electrochemical. So that can be done. Firstly, you have to know about this power law. So power law defines that this is the peak current, it is proportional, this is the scan rate, and it is the exponent of the scan rate. Whether it is 1, then the charge storage process is capacitive. If it is 0.5, then it is a diffusion process. And if it is in between 0.25, it means the mixed behavior is there. So you can do it, because as per this equation, you take the log of this. So it will be log I, and on this x-axis it will be the log nu. Nu is the scan rate. So you know that simply the slope will give you the value of b if you take the log of this equation. So by calculating the slope, you can find out the value of b. So this b will give you the idea that what is the charge storage mechanism involved in your device. Second thing is that after calculating this b, you have to find out the ratio. So ratio you can find out that with this done equations. So this is also similarly based upon that this capacitive current is directly proportional to the scan rate if it is capacitive process, and if it is diffusion, then it is the 0.5, means nu ki power 1 by 2. So if you do this, because already we calculate this, if you take the log of this, you divide this with nu 1 by 2, this equation will become IV upon nu 1 by 2, K2 nu 1 by 2 plus K2. Now you take the log of this and make the plot log I upon nu 1 by 2 versus nu 1 by 2. So the slope will give you the value of K1 and the intercept will give you the value of K2. So then you can calculate K1 and K2 both, and after putting them you can calculate the ratio. So that ratio is important, that how much contribution is capacitive and how much it is the diffusive. So that you can get it. This is the like 39% is the contribution is capacitive and 61 is diffusive. So accordingly at the different scan rate you can identify, and you can propose with the proof that my device has this one capacitance, a charge storage mechanism. So these are again these kind of the calculations about. Then you go for the GCD measurements, that will give you the idea about the charging time, discharging time, because that is important. In the energy storage device, two parameters are important: how much is the discharging time and what is the energy density. How you can have the large energy density. So we have to calculate this charge discharge. Then these are the some formulas, I will not go to details. That this is the cycling stability. Cycling stability means that I have the device, I run for a number of cycles. So how much capacity is retained? So it is expected as much as for the longer cycles, if it can retain the large capacity, so they are called the good device. So these are the, you see that impedance spectroscopy, it gives you the lot of information about the charge transfer resistance and all idea. And you see that these are the some of we have make the EDLC capacitors as well as to the pseudo capacitors. So as I told you that if you are using the carbon, so carbon is purely EDLC based. So if you are using both electrode are made by the carbon, so you are making the carbon based these capacitors. So we can make this carbon, this is the porous carbon. What is difference between carbon and activated carbon? So activated carbon means this is the chemically activated. Chemically activated means its surface area should be large and its pore size should be into the mesoporous range. So that is the thing. If you are using simple carbon, you will not get any capacitance, means capacitance will be very minimum. Suppose it was only the 10 farad, you can go it for the 200 farad until you will not do this activation process. So activation part is very important. So in this process we do the two kind of activation. First is the physical activation and second is chemical activation. So physical activation is to get the carbon, but the chemical activation is to make it porous as well as to the high surface area. So that is called the activated carbon. So we have used certain biomass and we can extract firstly the carbon by the carbonization process, and then this carbon is being, we have been chemically activated, and then we can make this is the porous carbon. You can realize that these are the pores, and in these pores the electrolyte ions, they can easily enter. So again the pore size, what is important? If pore size is suppose less than 2 nanometer, so the size is very less, ion will not enter into the pores. And if it is very large, then ion will enter and immediately they will come out. So discharging time will be less. So you have to optimize your synthesis parameters that, and what will be the synthesis parameter, you can have the pore size into the mesoporous range. So you see that firstly make this porous carbon, and then you, again the process is same. As I told in the starting, you simply firstly make to the carbon, do it the activation process, then you make the slurry. Slurry you have to make it with the mixing of all this 80-10-10 ratio of the PVDF and carbon black, and after that do the coating, and after coating you can make the this kind of. So these are the electrochemical results that we can having this. So you see that these are the CV curve, and they are almost linear. So it is indicating their EDLC nature. It is not pseudo capacitor. So these are about this. Similarly, we have been taken this amla leaves, and one more important thing is that in biomass the major part is the cellulose, hemicellulose and lignin, and they are present in the material from 70 to 96%. So you can extract a good amount of the carbon from any kind of the biomass leaf. So that is the thing, but important is that you are extracting the carbon, but what is the surface area and pore size, that is important. It depends upon your expertiseness, that how much good quality of the activated carbon you can prepare after extracting the carbon from these different types of the biomass. So similar thing we have tried of the different biomass materials, and then calculated their these capacitance and all this. So you see that in case the cycle is 25,000 cycle, this is only in case of this 25,000 cycle we retain the 95% capacity. It is not possible in case of battery. Battery only up to 3,000 cycles. This is 25,000. We have tried 50,000 also, even 1 lakh. You can go for the EDLC even 1 lakh cycles. So you can realize that how much will be the life. So life of these devices are very, this is large, long, and energy density 31 watt-hour per kilogram. It is less as compared to the batteries. So what is the idea is, these are the things that we are again making the device based upon these biomass. They are purely biomass based devices. We have used the chinar leaves also. One of my students is from Kashmir, so she bring these chinar leaves, and then you see that they have we have the surface area is 1867 meter square per gram. So it is very large, 1800 meter square per gram. So because of that, they are the large capacitance is there. Another thing is that because what we have learned that in case of these device of the purely EDLC, the life is good, but still the energy density is low. To improve the energy density, then we mix up some metal oxides like zinc, cobalt oxide, and this is carbon, graphitic carbon nitride. We have been make the composite, and similar kind of these we have been prepare the electrodes. And finally, so you see that here peaks is coming, oxidation reduction, because now they are the pseudo capacitors. So there will be the oxidation reduction process, and this is the you see that capacity cycle is 10,000. They are greater than to the battery, and if we see this, we have used here the gel electrolyte, not the generally people use the aqueous electrolyte KOH, NaOH, but there is a problem in the leakaging in case of the aqueous electrolyte. So we use the gel. It is of the PVA and NaOH, the mixing we make the gel, and that gel is being used as electrolyte, and also this gel is working as a you see that separator also. So no need of the separator to use if you are using gel electrolyte. So then we are energy density 39 watt-hour per kilogram in case of this device. Then similarly we have been tried some other RGO, ZnCO2O4. So this is the hybrid device, one electrode of activated carbon, another electrode of RGO, zinc, cobalt oxide. So that is being you see that it is made again a pseudo capacitor device, and we have been light up the 7 kind of these supercapacitors, like this 12 volt of the LED is being light up. Another you see that nowadays the Maxine is also a good material for energy storage applications. It is a new material in the category of these even supercapacitors as well as for the batteries. So this is a layered material. So in the layered material we do the firstly etching process, and we take out the aluminium layer out of that, and then these layers play the role that ions for the intercalation process of the ion. So because of that, this maxine is being formed. You see that stacking of the layers into this maxine. It is Ti3C2TX. So that is basically, this is the functionalization group, and aluminium we have been removed through the etching process, and then that we have been again making this kind of the LEDs. They are being glow by using the, and you see that contribution is, in case of the maxine, is again it is maxine because there is a metal are there, so some redox reaction will definitely occur. So it's a hybrid device. The contribution will be there, electrostatic as well as electrochemical. So that has been calculated, and then to see the practical applications, we have been light up certain LEDs, LED red panels by using these maxine based capacitors. So these are the some of the device we have fabricated the cells for the different applications. So thank you so much for listening.
Thank you very much for the very interesting talk. And now it's open for the question. Any question? Okay. Okay, so question will be taken at lunchtime, and now we basically, are there any question? Burning question, we can have one or two.
One or two question you can ask if you have any doubt.
So one question, just for ignorance
Yes,
of this
yes.
all supercapacitor. Like if you see the Plasma Research Institute, all they use the big capacitor to create the discharge in the plasma. Do you think the future the supercapacitor can be used there?
Supercapacitor can be used because if the purpose for you see that if you need a very high amount of the energy,
Yeah.
and if it is required instantly, so naturally
Yes,
you need the power density purpose. But in case of the plasma generation, there is no need of the portability. So these energy storage device only if the purpose is portable. Otherwise, there are a lot of options are available. Why we have to go for supercapacitors? So portable applications we have to do, and power density is already of the good of supercapacitor, so they can be used. But generally people don't use because generally we use them for the portable device.
Portable, okay. Yeah, thanks. Yeah.
Sir, very nice presentation of supercapacitor. Like in quantum we use superconductor. So the superconductor capacitor, like you elaborate, can it use for the quantum storage?
No. Actually, you see that the purpose in the superconductor or supercapacitor, they are totally different things. You know that what is the mechanism there. So there we are using the resistance being minimized, and it is because of the movement of the electrons will be through the copper pair formations, not as an individual. But here is that how you can store the charge polarization is important. So they are entirely different. So we cannot do that with the help of the supercapacitors, and we can use it for. And the quantum, you are talking about this quantum storage, so that is it is not related to this charge storage phenomena, electrochemical. That is about the movement of the spins. So because of that, it will be the entirely different phenomenon.
Because sir, in classical computational, we use either magnetism in hard disks and electrons in SSD.
So there will be the quantum conductance that will be.
We are running short of time, so
Okay,
you
sir.
can discuss
Thank you,
during lunch time.
So next we have Ashwini Kumar. Ashwini Kumar is a distinguished researcher and industrial leader with the extensive experience in the growing the high quality single crystal diamond using the advanced 2.5 gigahertz and 915 megahertz microwave CVD system. As a founder and CEO of the Pristine Diamond Private Limited, he has manufactured state-of-the-art MPCVD reactor and provided the end-to-end solution for setting up the complete CVD facility. His experience span epitaxial growth of the large SCD plates for the semiconductor application, proficiency in the PVD technique, and experience in multiple characterization tool. Prior to leading the Pristine Diamond, he served as the associate professor at Bennett University and held the senior scientific role in the diamond industry following the postdoctoral research at Seoul National University and Kwang Puk National University. He earned his PhD at Nanotechnology, Material Science and Engineering from the Indian Institute of Technology, Roorkee, and Dr. Ashwini Kumar. So you can have any question answer to him.
It will be kind of interactive session.
Yeah.
So hello everyone. I hope I am audible. Thank you very much for the opportunity. And most probably this is an interactive session, not a talk kind of lecture, where all, especially it is for students only kind of thing. And if you have any questions related to your, your goals, whether you would like to move on in your career, then you can open up. So before that, I would like to brief you about my journey as a founder of Pristine Diamonds or as a founder of a startup. So I did my PhD from IIT Roorkee in 2009. Before that, I was the alumni of this university, and thankful to all great teachers, and through them we learned a lot. And then I have spent a couple of years in Korea with Samsung, developing some semiconducting, substrates and devices. Then I came back and joined Bennett University, served as associate professor. In 2021, I quit the job and started my own company named Pristine Diamonds. Initially, thank you. Thank you so much. So initially, I started making microwave plasma chemical vapor deposition systems, which is used to grow diamonds. When we talk about diamonds, then generally we think that it is natural diamonds, and other than that, we think these are synthetic diamonds, or the mimic diamonds, but it is not true. We can grow diamonds in the lab, and with the same compositions, with same chemical, physical, every property same, even better. So it can be grown via two methods: HPHT, high pressure, high temperature method, where the environment of the cavity is maintained very similar to the environment inside the core, earth core, where the natural diamond is being developed. But there is also another technique where we use the gas phases, the methane as a source of carbon, hydrogen as a etchant, and any other gases, and we develop diamond. The beauty of this diamond is that you can control the defects. So generally when we say diamonds, then in that case, every one of us think that it is a piece of ornament, but it is not true. Nowadays, diamond is accelerating and having its most potential properties as a semiconducting material because of its band gap, because of its, you can develop color centers or NV centers, which can be used as the next generation qubits, where the electron trapped into this defect can act as a spin up, spin down, can be in a superposition position. You can create those kind of defects, can manipulate the spin state, can read out optically, and beautiful thing is that these states can be controlled at room temperature. When you look at the quantum computing, then generally the data centers are being stored or running at a very low temperature, a huge consumption of power. But nowadays, the diamond has gained so popularity, especially in these kind of applications. So we are developing these kind of qubits, also granted grants from government, and so forth. So what I understand is that if you are going through this phase of life during your academics, I understand mostly we aim for the job or that kind of, sort of career choices. But my advice is that please focused onto skill development rather than job. First, if you are very much skilled and excelled in your thing, then you should not be dependent on any kind of job. There are lots of technological advancement, lots of initiative taken by Government of India, as well as lots of upcoming technologies where you can have your thoughts, you can develop the products and can match up with the upcoming technologies. Especially not the existing technologies. As a researcher, as an academician, we have to look forward for the technologies that are supposed to be coming after 5 years or the 10 years, the upcoming technologies, not the technologies that are outdated or that are, at par or with the current edge of time. So that's all. Of course, being an entrepreneur had its own challenges or own journey, but at the same time, if you look into the overall results, then it is very satisfactory. You are contributing to the country, to the self, creating employment, and there are lots of things that always you are flexible to develop new things, new technological instruments. So, and in this journey, most important thing is that you are always connected with the upcoming technologies. So therefore, so here I end my overall experience. If you have any questions, you feel free to ask. Yeah. So, thank you. Yeah, please.
Hello, sir. Myself Bindu from Central University of Rajasthan. I am a MSc student. सर मैंने MSc के साथ साथ जो इंटर्नशिप होती मैंने लिथियम आयन बैटरीज पे इंटर्नशिप की थी 1.5 मंथ की एंड मेरा प्रोजेक्ट हुआ है वहीं से सेंट्रल यूनिवर्सिटी से वो था कैटलिस्ट मटेरियल पे. सर मैंने 1 साल प्रोजेक्ट किया है कैटलिस्ट मटेरियल पे और हाफ मंथ ही नहीं 1.5 मंथ मैंने इंटर्नशिप की है लिथियम आयन बैटरीज पे. सर मेरा ज़्यादा इंटरेस्ट मुझे लगता है कि लिथियम आयन बैटरीज पे, बट उस पर मेरे को अपॉर्चुनिटी इतनी मिल नहीं रही है एंड मेरा कम इंटरेस्ट है, बट मैं उसके साथ काम कर रही हूँ, उसमें ज़्यादा अपॉर्चुनिटी मिल रही है. तो क्या मुझे उसके साथ जाना चाहिए या मुझे ज़्यादा इंटरेस्ट है?
So, see, my perception is very different in terms of technology. If you look at the core, right, the core of the materials, if you understand the materials, if you understand its properties, if you understand the characterization as well as the deposition techniques or the multiple routes, then this is only matter of applications. Where would you like to apply these materials? But more or less the core remains same. For an example, I was making devices in Korea for DNA sequencing, right? If I say DNA sequencing, because we are physicists, it doesn't make sense that how a physicist can work on a project where DNA sequencing is the primary object. But the core is that there we were making solid state devices. It consists of wafers, it consists of holes, multiple layers, multiple tunings. And then application is only the DNA sequencing. So same happens with the lithium ion batteries or nanomaterials or supercapacitors. The core physics, the core idea is same. Only application is different. So I think that our intention should be to understand the material and how can we tailor the properties, how can we use it for different applications. So I hope that you understand that the core idea is to develop the core strength, not focus yourself much onto applications, right? So the thing that you have mentioned is very much application, that these are lithium ion batteries. But if you look at the core, then you are developing certain materials, certain electrolytes, right? And the similar kind of phenomena you can see in supercapacitors also, but with different composition and properties. So that is my answer, that please do not focus especially on any particular application side. Please focus on to strengthening your core. Yeah.
Sir, I have one question. First of all, I want to introduce myself. My name is Dr. Vijit Pandey. I did PhD from Department of Physics, AMU Aligarh. I am also running a startup named CISC R&D, that is Scientific Analysis by Indian Research, which is working on the semiconducting physics, and we also produce the semiconductor devices and semiconductor material. and we also give the facility heat treatment annealing for semiconductor material and heat treatment. Sir, I am asking one question that some of the clients related to diamonds and jewelers, they approach me towards diamond annealing and stone annealing. Sir, your startup is providing such type of facility?
Yeah, we are providing annealing also.
Sir,
So, yeah.
What is the temperature up to that?
No, so think that way. That, for example, when we say annealing in diamond,
yeah,
then there are two types of annealing available. And generally three, you can categorize into three categories. The first is HPST annealing, where high pressure, high temperature been induced, where temperature is roughly 2100 degrees centigrade. 1700 to 2100 degrees centigrade or even 2200 degrees centigrade you can maintain, and the pressure is very huge, 700 bar or maybe 500 to 700 bar, which is a huge pressure. It is not a gaseous pressure. It is generated by certain, hydraulic press and all this. This is one annealing. We can arrange for such annealing. Another annealing is vacuum annealing, because in environment, if you anneal the diamond, the graphitization chances is enhanced. So the environment must be in vacuum. So that kind of annealing can be performed up to 1200 to 1300 degrees centigrade. The purpose of this annealing is generally that when we are creating NV center diamonds, so NV center means that there is a nitrogen atom into the diamond lattice associated with one vacancy. And this phenomena cannot happen, all of a sudden. So therefore, sometimes we take the path where we implant nitrogen, then we radiate it with electron, creating vacancies, taking away the carbon atoms, and then the annealing required to combine them, the mass transfer and all these things. Such annealings are generally performed ranging from 900 to 1300 degrees centigrade. That arrangement we have with us.
Okay, sir, what is the scope about in India at industrial level of diamond annealing or stone annealing? If we start as a type of a startup,
I don't think it is much.
Okay.
The reason is that in India, the diamond manufacturer, mostly those who are interested in growing lab-grown diamonds, are mainly focused on to gem applications. The people who are making, using diamond as a technical product are very limited. And those companies generally have their own facilities.
Yeah.
And when you are saying about, if you are considering the gem grade annealing, then you require HPST, which is a huge and giant machine, and plenty of available in Sudan. So I don't think there is any scope in that area.
Okay, and the second question is currently I and my startup is also in a struggling phase because it is two initiative. Sir, is there any way to collect funding from semiconducting private companies?
No, unfortunately. The reason is that, see, anyone who shows interest in your company, either there must be a product. That product must fit their requirement. That is one thing. Another thing is that if you don't have a product, but you have a roadmap and a good idea and certain basic primitive experiments, then you can go for seed funding to investors. Generally, the semiconductor companies in India are launching at a very large scale. If you look at the Tata, Micron, Lam, right? All are coming up with huge investment, 1 lakh crores and so and so. They have their collaborations at that level. Also, they are imparting technologies from abroad directly and implementing here. So, scope for such startups to get embedded into that structure system is not easy.
Yes, sir.
And unfortunately, right now, there is not many semiconducting related companies at very tiny scale where you can be associated up with. So your product must be market fit. That is one thing. And in a startup, there are few things, especially in technical startups. The first, market moves faster than the lab. That is one thing. That what we are doing in lab, market already did it couples of years back.
I face it.
So that is one thing. Secondly, team is very, very important. Even then, you can say that the technology is essential and necessary, but not sufficient.
Yes, sir.
So team is the second thing. Third, the product, the research fund, or whatever you are, spending in your company, you should make sure that your product that you are about to make is market fit. And what are the market share? What is the market size? How much revenue you are expecting in a certain period of time over the period of time. So the market fit is the third thing. So these are the scenarios in here.
I can understand.
All the best for your venture.
Thank you, sir. Currently, we are also producing a large level of nanoparticles for pharmacological company also.
Okay.
Main product was this,
Okay.
but now we are moving for semiconductor devices also. So that time we are facing struggling,
Yeah.
but we are looking something else.
So all the best. Yeah.
Thank you, sir.
If you need any help, please contact.
Oh, okay, sir. Thank you, sir.
Yeah. So thank you. Yeah. Thank you, everyone. Yeah. All the best for your future. Yeah.
Yeah, thank you very much for Swani Kumar for a nice discussion.
Is Mr. Tushar Kumar present? Mr. Tushar Kumar from Graphic Era University present? Okay, please wait. No, you need to wait. Please wait. And okay, Dr. Rahul is outside, so
10 minutes. After that,
10 minutes. Aditya Gurjar? Aditya Gurjar? Is Aditya Gurjar present? Aditya Gurjar from University of Rajasthan.
So the okay, the next talk is Satyendra Pal Singh, and she is from SSV College, Hapur, and she is going to talk about the enhanced. Talk about the enhanced solar driven photocatalysis using the silver zinc oxide geo nanoworm for the environmental application. Sir, Dr. Satyendra. Yeah, 10 minutes.
Okay. Enhanced solar driven photocatalysis using AG-DOP ZNO geo nanoworms for environmental applications. Next. I will skip next. The outline of my talk is introduction, objective and solutions, photocatalyst and emerging technology, materials used for photocatalysts, materials used in this study, synthesis process, results, and last one is the conclusion. Next. Introduction. Nowadays, pollution is one of the main problem. It is not affecting human beings also, it is affecting animals also. We see pollution in the drainage systems, in the rivers, and in the environment outside. Most of the pollutants are inorganic chemicals such as lead, arsenic, nitrite, and nitrate. Some organic dyes like methyl or orange, crystal violet, Congo red, methyl blue, and rhodamine B also add in this process, and this contamination of water also takes place due to antibodies and antibiotics and microbial contamination. Next. The effect of this contaminated water is that it affects human health. It causes so many diseases, and it also affects environment and agriculture. In case of agriculture, infertility takes place due to contamination, and soil is also affected in this process. Next. Objective and solution of this contamination. Objective of wastewater treatment: to improve quality of wastewater, elimination of pollutants, toxicants, and many other contaminations, preservation of water quality of natural material resources to make wastewater for usable purpose. Technologies which are used for this purpose are these one, but we are concentrating on photocatalyst. Next one. Photocatalyst, an emerging technology. Photocatalyst, a substance that uses light to facilitate a chemical reaction to degrade pollutants in the contaminated water. In this process, we use redox reactions to minimize or to neutralize this pollutants. So, photocatalyst is a very cost-effective technique to get contamination-free water. Next one. The materials we are generally used for as a photocatalyst are photocatalytic powder, photocatalyst thin films, and some inorganic materials and some composite materials. Organic and hybrid composites are also used. Next one. Materials which we are used in our study are graphene oxide, ZNO, and Ag, silver. Why we are using these three types of materials? Graphene oxide has a active role in photocatalyst by decreasing the aggregation of ZNO particles and acting as electron acceptor material, handling the electron hole recombination. Due to 2D structure, abundant surface oxygenated functionalization is possible in this graphene oxide. Graphene oxide also induces the formation of oxygen vacancies in ZNO, improving its photoresponse. ZNO has been used as an effective photocatalyst due to its higher absorption efficiency. Ag, which we are doping, which we are using as a dopant in this study, acts as an antenna for visible light, which boosts the efficiency of the catalyst. Next one. Synthesis process. Actually, we used hydrothermal process for the synthesis of this photocatalyst. And we generally use two types of precursors. For ZNO, we used ZnCH3CO2 2H2O, and for Ag, we use AgNO3. Next one. These are the results. First one is the XRD. In XRD, we confirm the presence of ZNO, graphene oxide, and Ag. Next one. This one is the UV visible spectra of the different samples which we synthesized. From UV visible spectra, we calculated the energy band gap for our samples, and the band gap of GO, ZNO, A1 is 0% Ag, A2 is 3%, and A4 is 5% Ag. And we get 3.25, 3.33, 3.23. Here, this energy band gap decreases from 3.23 to 3.04 in case of 0% to 3% Ag doping, but it increases in case of 5% to 3.15 EV. Next one. This one is the FPIR spectroscopy of ZNO Ag nanocomposites, and this also signifies that the samples we got have different materials like GO, ZNO, and Ag. Next one. This one is the FESAM. The FESAM images of GO, ZNO, and AgNO are shown in above figures. The FESAM of ZNO shows the flanky-like structure. The FESAM of ZNO shows a nano antennas-like structure. The FESAM of ZNO GO shows aggregation of nanograins of ZNO on the flanky structure of graphene oxide. Next one. The FESAM image of 1%, 3%, 5% doping of Ag in AzGO nano composites are shown in other figures. In 1% doping, we get the big sheet in thread-like structure, while in case of 3%, we get nano worm-like structures where Ag aggregated on the ZNO GO sheets. While in case of 5%, a nano-like structure is now found, but there is a more aggregation of Ag so that this structure is not suitable for our case. Next one. This one is the index, and different elemental percentages are shown on the right side. Next one. This one is the TAM, and the overall the final conclusion which we have drawn from this TAM is that the TAM as SED and EDS analysis collectively confirm that Ag is successfully doped in ZNO-GO hybrid structure, enhancing crystallinity, purity, and structural integrity suitable for photocatalyst activity and gas sensing applications. Next. This one is the STAM mapping. Here also we get the conclusion that the successful formation of AzGO nano composites and confirms the Ag is uniformly integrated into the ZNO-GO network in the doped sample. Next one. This one is the XPS survey of our samples. The conclusion which we have drawn from this XPS survey is that the metallic Ag is successfully doped in ZNO-GO nanocomposite, and this Zn retains its +2 oxidation state and presence of oxygen rich surface groups which contributes to the improved charge separation and enhanced photocatalytic activity. Next one. Now we are using this nanocomposite for photocatalyst. First one, we are using it for methyl blue, and in this case we are using 1 0%, 1%, 2%, 3%, 5%. We got excellent performance in case of 3% doping of Ag, nanocomposites. Next one. Next is the case of rhodamine B. Here also we get the excellent performance in case of 3% atomic percent of Ag. Next. Now we are using this nanocomposite for as a photocatalyst for ciprofloxacin. Here also we get the repeated result in case of 3% Ag dot composite. Next one. We for photocatalyst managements we use this formulae. Dye percentage is equal to 1 minus Ct upon C0 into 100. This C0 is initial concentration of dye and Ct is at a particular temperature at a particular time. Ag dot ZNO showed enhanced photocatalyst efficiency of 96% for MB dye and 97% for rhodamine B dye and antibodies under photo irradiation of solar irradiation of 60 minutes for MB, 90% for rhodamine B and 180 minutes for CPF. Next. So this is the mechanism which involves in this photocatalyst. The redox and oxidation reduction and oxidation process takes place and we get a clear water and all the methylene or rhodamine B or CNF is now fully neutralized. Next one. Photocatalytic mechanism of ZNO-GO-Ag. The photocatalytic mechanism ZNO-GO-Ag involves the following. Addition of graphene oxide to photocatalyst system enhances the photocatalyst efficiency of ZNO under visible light irradiation. The large surface area of GO can contribute to the effective adsorption of rhodamine B, MB, CFP molecules on the photocatalyst surface and increases the formation of pi star interaction between the molecules of different pollutants. Ag nanoparticle doping in ZNO crystal lattice could minimize the recombination of the excited electrons in the conduction band with the holes in the valence band, which would increase the production of oxygen radicals by reaction with oxygen molecules, leading to the oxidative degradation of these pollutant molecules. Next one. Now this one is the conclusion of this study. First one is we successfully synthesize Ag.ZNO-GO nanocomposite. Next one is the structural formation. The microstructural characterization confirms the formation of nano-worm-like structure for these nano composites. Band gap tuning. The band gap Ag decreases from 3.23 eV at 0% Ag to 3.04 eV at 3% Ag due to defect induced energy states that Ag doping then slightly increases to 3.15 eV at 5% atomic percent of Ag because of the excess carrier concentration and defect saturation. Optimized composition. The AZ-ZNO 3% of silver nanocomposite exhibit the lowest energy band gap and highest photocatalytic activity owing to its optimum charge carrier separation and enhanced electron mobility. Superior photocatalytic property. 3% Ag-GO achieves the fastest degradation rates completely in MB, RB and CP removal within 60, 90 and 180 minutes respectively under solar irradiation. High removal efficiency. The maximum CPF degradation up to 98% was observed for Ag-GO 3% of Ag. confirm its superior efficiency compared to other compositions. Last one is the environmental relevance. The AG.ZNO-GO nanocomposite, particularly at 3% Ag, demonstrates high solar energy utilization and strong photocatalyst stability, making it suitable for efficient photocatalyst for environmental wastewater treatment. Next one. Thank you very much.
Time we can have one question and then remaining can discuss during the lunch time. If you have any burning question, okay.
Sir, I have a small question.
Yeah.
Which characteristics of this material contributes to its that nomenclature, nanoworms?
Nanoworms.
Yes. Like
Actually, the temperature during the synthesis of nanomaterials confirms its shape, at which temperature we will grow these types of materials.
And sir,
So temperature plays a very crucial role in case of nanosynthesis.
and sir, how you are getting the confirmation that this nanocomposite is formed?
I have shown you FESM. In FESM, there is structure is shown like worm, nanorods like
No, sir,
nanoworms.
how the
I think you can discuss more in the lunch time. So let's go to the next speaker. Yeah. Okay, so now the Dr. Rahul.
Thank you.
Is there around Dr. Rahul? Is Dr. Rahul around? Dr. Rahul from Gurgaon University, Haryana, and he's going to talk about next generation IGO couple nano composition for the advanced water purification, biomedical application, and environmental remediation. So, Dr. Rahul. Kumar. Kumar talk, and he is the graphic era deemed to the University of the Dehradun. The title is the optimization of the supercapacitor performance via the thermal control flower like MOS2 nanosphere.
Good afternoon, everyone. I'm Tushar Kumar, research scholar from Graphic Era, deemed to be University, Dehradun, and today I'm here to give you a presentation on my research paper titled Optimization of Supercapacitor via Thermal Controlled Flower-like MOS2 nanospheres. So this is a basic content of my presentation, the topics that I will be discussing in my presentation. When we are working in the field of supercapacitors, so the first question that comes to anyone's mind is that why do we need supercapacitors? As we all know that there is a rapid energy consumption globally and environment impact due to traditional energy resources. So in today's world, we need some advanced energy storage systems, and materials plays a key role in the determination of these energy storage systems. Like some example of materials are MOS2, WS2, WAC2, etc. I have mentioned MOS2 as I'm working on it. What are supercapacitors? Basically, supercapacitors are energy storage devices that bridge the gap between traditional capacitors and batteries. So they store charge electrostatically like a capacitor, but they can store a very large amount of charge. And the reason for this is because of its unique electrode design and the electrolyte that has been used. So types of supercapacitors. Supercapacitors are basically divided into three types. First is the EDLC, electric double layer capacitor, which is further divided into graphene activated carbons and so on, and the pseudo capacitors that is divided into traditional metal oxides and conducting polymers, and the hybrid capacitors. The main thing that determines them is their charge storage mechanism. Like EDLC stores the charge electrostatically, while the pseudo capacitor has a charge storage mechanism of Faradic redox reaction, whereas the hybrid capacitor has both the properties, like it stores Faradically and also electrostatically. This is a very good example of the supercapacitors. It is the China electric bus. So the supercapacitor is basically installed at the top of this bus, and when the bus comes to a bus stop, in the few seconds in which the passengers come out of the bus and new passengers take the seat, so the supercapacitor gets charged so that it can travel the distance from that bus stand to the another bus stand. So this is a very good application of supercapacitor at present time. Basically, it's takes few seconds just to get charged. So basically, this is a good example. So like I'm working on molybdenum disulfide. So it is its chemical formula is MOS2. It is a layered structure, and it in this one molybdenum atom is sandwiched between two sulfide atoms, and it is held together by a weak van der Waals force, and its crystal structure is hexagonal. So the synthesis method, I have used the hydrothermal synthesis method, in which we used a Teflon-like autoclave of stainless steel with a Teflon-lined jar, in which we basically in a distilled water we mix our precursor material, and we place it in a muffle furnace for at 180 degrees Celsius for different time intervals. Like I have mentioned the time intervals, I have done it for 4 time intervals, for 12 hours, 18 hours, 24 hours and 30 hours. But the thing is that I'll be giving the reason in my further slides. I have given the results for only three time intervals, that is 12 hours, 24 hours and 30 hours. Basically, the reason for is that 18-hour sample has not been reported here because it has a lot of impurities, and these impurities were confirmed by the XRD plots of this. So the next step is the drying of the solution to get the powder form of it, and after that this powder was characterized for different morphological and electrochemical, for studying the morphological and electrochemical properties. So morphological analysis. In the morphological analysis, I have used 3 characterization techniques, that is XRD, X-ray diffraction, FESEM and the EDEX. So there I have named the samples MOS to 12 hours, 24 hours and 30 hours. So here the XRD of MOS2 that was made while using a hydrothermal method. So it gave its peak at the angles, like we can see over here at 13.5 degrees, 33 degrees. The fourth one is at 39.8 degrees, and fourth is at 59 degrees, and it basically corresponds with its crystallographic pattern, crystallographic phase, like 002, 100, 103, 110. as I'm talking about the different calcination durations that I mentioned, the effect of calcination durations you can see in these graph. Like when I have increased the temperature, the broadening of the peak, basically the peak gets broadened. Like we can compare all the three, taking MOS to 12 hours as a reference, we can see a broadening of peak in the 24-hour sample and more broadening in the 30-hour sample. And finally, the crystallite size was calculated using the shear formula, that is D is equals to 0.9 lambda upon beta cos theta, and it came to be 12.89 nanometers, 6.01 nanometers, and I remember 30 nanometers approximately. So these are the FSM images. Like the this image over here, it confirms a marigold flower like morphology. Like this is a basically a marigold. We can also say it a tegot like morphology. Like I'm working on in the fields of supercapacitor, or if we work in the field of supercapacitors, batteries, capacitor, the main thing, the one thing that we need to keep in our mind is the porosity. So as we can see that the most porous sample is this MOS to 24-hour sample. When taking it as a reference, if we compare this 12-hour sample and 30-hour sample, we can see that there is a reduction in 40%, about 40% in the porosity, and in this sample there is a reduction in 20 to 30% porosity. And this marigold-like morphology is because of two reasons: the method that has been used, the hydrothermal method, and the precursors that has been used. Basically, the precursors that were used were molybdenum, sodium molybdate dihydrate, and thiourea. The first one was the source of Na2MOO 2 negative and H positive, while thiourea was the source of the sulfur. So that's the reason we got this marigold-like morphology. The third morphological characterization is the EDX, or the energy dispersive X-ray spectroscopy. So here the elemental composition is confirmed by this energy dispersive X-ray spectroscopy, where we got the peak of molybdenum and sulfur. If we take basically the morphological characteristics like increased surface area, porosity, when they are coupled with the environmental analysis, we get that there is a basically enhancement in the electrical and the basically in the electrical and the supercapacitor properties. So all this was confirmed by this energy dispersive X-ray spectroscopy. Now the electrochemical analysis. In the electrochemical analysis, we have done three tests. First is the cyclic voltammetry, second is GCD, galvanostatic charge discharge, and EIS. So basically in the GCD, for the three sample, it is that when basically first I would like to tell how we have done this electrochemical analysis. So first we made the electrodes of our material. For making the electrode, we use three things. Our active material, that is MOS2. Its concentration was 80%, and N-methyl 2-pyrrolidone, whose concentration was 10% of the total powder that we have made, and third one was the carbon black, that was 10%. These were mixed together, and after that, using the blade, it was coated on the electrode, and after that the CV was performed in the 1 molar H2SO4 solution. So in the CV, we can here see that from 1 to 20 millivolt, here is a rectangular like basically a rectangular like shape, but when this scan rate was increased from 60, then 100, then 150, then there is a leaf like morphology. So as the
निकाल इसे निकाल हटा लैपटॉप हटा यहाँ से हब का इशू तो कल भी होता ना बात ये मैं कह रहा हूँ समझा मेरी बात को वो वाला कैप्चर लगा
not be calculated from the CV. The reason being that for energy density we need the discharge time, and that we get from GCD. While these are the GCD graphs here. This GCD was used to calculate the. I have used both CV and GCD to calculate the specific capacitance and the power density, but this was also used to calculate energy density and charge and discharge times. Here we can see that here's a when I'll explain it when the current density was increased from 1 to 5, we can see there was a decrease in the discharge time, and for due to this decrease in the discharge time, there was a minimum amount for the ion to get accumulated to the electrode. So and when the current density was higher, when the current density was lower, then at that time there was a more time for the ions to accumulate at the electrode, and this is the reason for the increase in the capacitance and the different values of the parameter that has been calculated. These are the calculations for these are the specific capacitance that I have calculated, and for all the three samples with energy density and power density. We can see that with the increase in standard, the specific capacitance decrease, as I have told in my previous slide. Basically, EIS was used to calculate two things. Mass transfer resistance and the electrode resistance. So the values of this are given in these circuit, and I think these are all visible here and here. So here we can see in the low frequency region there is a curve, and after that there is a straight line. So this is due to the interfacial charge transfer resistance, where in the low frequency region. In the high frequency region there is a curve, and after that a straight line. This is due to the mass transfer resistance, and here we can see that there is a horizontal downward tilt in this graph. Here we can see that with the decrease in z double dash, that is the imaginary part, there is an increase in Z dash value, and this is because of the inductive behavior. It was because of the inductive behavior, and this inductive and this happened because there was a current lags the voltage because of inductive behavior in the system. So as I have told, that XRD confirmed the hexagonal phase of MOS2. Average crystallite size are given in 12.89, 30.1 and 6.41 respectively for the samples. These SEM images, it is FESEM images, it gave the marigold-like structures with a thickness of 20 nanometer. EDEX confirmed MOS2, molybdenum and sulfide, while CV and GCD were used to calculate the specific capacitor, energy and power density, and EIS was used to find the charge transfer resistance. So all these results reveal that MOS2 is an ideal candidate for the supercapacitor applications. So these are the references that I've taken for my work. I would like to thank my department for giving me the equipment and the resources for performing experiment. I would like to thank Mr. Somdat and Dr. Ramesh Chand of Institute Instrumentation Center, IIT Roorkee for structural characterization, and Vinay Kumar, Department of Physics, CCS Haryana Agricultural University for electrochemical characterization. I would also like to thank Department of Physics, CCS University Meerut for organizing this conference, where I got the opportunity to present my work. Thank you. So if there are any questions, so you can ask me.
We can have one question and then we go for lunch.
Hello. So nice presentation by you. So
Thank you.
how we can increase the energy density more, and what is the penetration depth of the electron beam in the SEM?
For increasing the energy density, we can do it by working on the porosity. If we increase the porosity of our material, then the energy density will increase, but to a certain extent. If the porosity is very much high, then at some point of time the energy density will decrease. And about the SEM, it is like if the thickness of the sample is in microns, then I think the electron beam will penetrate to a depth of 10 nanometers. If I guess if I'm right.
Thank you.
Let's thank all the speaker and let's go for the lunch. Okay, just wait.
Thank you. So, those who have poster presentations, please put your poster during lunch time, and from 3 PM onwards up to 4 we will have the poster presentation. यदि कोई बाहर भी है उसको बता देना, अपना पोस्टर लगा दे लंच टाइम में, और 3 बजे से पोस्टर प्रेजेंटेशन होगा और उसमें ज्यूरी आएगी. यू हैव टू बी प्रेजेंट देयर ड्यूरिंग द ज्यूरी विजिट. ओके, थैंक यू. और अभी रुकिए, अभी सर का फेलिसिटेशन होना है. आइए.
Yes, sir.
जरूरत नहीं है, वो मुझसे बात हो गई है, 2 बजे आएगा. हाँ, वैसे भी सारा ठीक ही है.